Welcome back to the Snoozy Scientist, a calm corner of the universe where curiosity and science drift together to put you to a calm sleep. Tonight, we're stepping deep into the restless heart of our world, and there, beneath America's most visited national park, lies one of Earth's greatest ticking clocks, Yellowstone. On the surface, it is a place of forests, mountains, and geysers, a wonderland of steaming springs and rising plumes. But beneath that beauty rests something far greater. Yellowstone is not just a volcano, it is a supervolcano, a sleeping giant with the power to change the climate of the Earth overnight, with eruptions thousands of times more powerful than those we call normal. Its vast hidden chambers of magma stretch beneath the ground like a sleeping ocean of fire, silently waiting. Scientists warn that its eruption could have a devastating impact, not just on America, but on the entire world. And the haunting reality is that they are unable to provide a precise date for a future eruption. While Yellowstone has a long history of eruptions, the most recent major one was over 600,000 years ago. Even though there are currently no signs indicating an imminent eruption, scientists continuously monitor the volcano for signs of increased activity. But the questions still linger. What makes Yellowstone so different from any other volcano? What would really happen if it erupted tomorrow? And why do scientists consider it a greater existential threat than even an asteroid strike? Tonight, we'll step carefully into that story, not to alarm, but for wonder and curiosity, to understand the full power of this hidden colossus and the fragile world that rests above it. But before we begin, I'd love to know, where in the world are you listening from tonight? Whether you're curled up under blankets, swaying on a night train, or simply letting your mind drift as you fall asleep, it's always wonderful to imagine this little community scattered like stars across the globe. If you find comfort in these gentle science stories, it would mean a lot if you could give this video a like and maybe even subscribe. Thank you to everyone who's already joined this snoozy corner of the internet. It's because of you that these calm little journeys can keep going. So now, take a slow, easy breath, let your shoulders soften, and together, let's begin the story of why Yellowstone scares scientists more than asteroids. Yellowstone is often imagined as a towering volcano, a cone of rock that might one day shatter the sky. Yet what lies beneath America's most visited park is something far stranger and more vast. Yellowstone is not a mountain at all. It is a caldera, a great scar in the Earth's crust left behind by past cataclysms. From the ground, it can be hard to see this shape because time and forests and rivers have softened the edges. But to geologists studying its contours from above, the land reveals a sunken basin, a depression miles wide, where the earth once collapsed after ancient eruptions emptied its depths of molten fire. This extraordinary structure was born from a mantle hotspot. Deep below the crust, far beneath the shifting plates, a column of scorching rock rises slowly from the mantle. It is not fixed to the surface, but as the North American plate drifts westward, it carries the land across this stationary plume of heat. Over millions of years, the hotspot has burned its mark into the continent. Each time the plume pierced the crust, it unleashed unimaginable eruptions and left behind a trail of ancient volcanic scars stretching from Oregon to Wyoming, like footprints of fire across the land. Yellowstone is where the hotspot rests today, and it is here that the scale of the system becomes almost impossible to comprehend. Beneath the rolling plains and mountains, hidden from sight, lies one of the largest reservoirs of magma on the planet. Seismic surveys and satellite imaging have revealed a chamber so vast that it dwarfs entire countries. It stretches for tens of miles across, a world beneath the world, filled not with solid rock, but with molten stone and crystal mush that shifts and seethes slowly with the heat of the mantle below. To imagine it, one must think of an underground ocean, a sea of fire beneath the crust, so large that it defies easy comparison. At the surface, however, Yellowstone hides its terrible heart beneath a mask of beauty. The park is famous for its geysers, fountains of boiling water that erupt rhythmically into the sky. They are playful, almost whimsical, but each one is a reminder of the colossal heat beneath. The geysers are powered by water trickling down through the ground, meeting rock so hot that it flashes into steam and bursts upward in sudden fury. Old Faithful, the most celebrated of these geysers, erupts with such precision that visitors gather to watch its clockwork performance. Yet every plume of white steam is also a whisper from the depths, a small sigh from the restless chamber far below. The hot springs are no less extraordinary. Pools of water shimmer in vivid colors, painted in blues, greens, and fiery reds by the heat loving microbes that thrive at their edges. The grand prismatic spring, larger than a football field, gleams with bands of color so bright they can be seen from the air, as if the earth had opened its eye to stare back at the sky. Tourists marvel at its beauty, but to geologists it is also a vent, a window into the immense furnace beneath the park. Then there are the boiling lakes, bodies of water so hot that mist rises constantly from their surface. Their names are warnings in themselves: the Firehole River, the Dragon's Mouth, the Mud Volcano. They bubble and hiss, releasing gases from the underground system. The smell of sulfur thicken the air. Standing beside them feels like standing near something alive, as if the ground itself is breathing. Everywhere in Yellowstone, the surface pulses with heat, from the hissing fumaroles to the steaming terraces of mineral deposits. It is a landscape of paradox, breathtaking in its beauty and unsettling in what it reveals. For beneath the lakes, the forests, and the mountains is not quiet rock, but a superheated cauldron, a caldera unlike almost any other on Earth. What we see as a national park is also the rim of a colossal wound, healed over time but still alive with fire. The story of Yellowstone is one of disguise. To the millions of visitors who hike its trails each year, it is a place of wonder, of wildlife and wilderness. But to those who study the earth, it is also a reminder that beneath this tranquility lies a force powerful enough to change the climate of the entire planet. It is this hidden duality, the surface beauty masking the unseen danger, that makes Yellowstone both a jewel of nature and one of the most closely watched places on Earth. And as we begin to understand its structure, its hidden chambers, and restless heart, the story of Yellowstone deepens. For this caldera is not just a feature of the landscape, it is the stage upon which some of the greatest eruptions in Earth's history have already played out, and where the memory of fire still lingers. Beneath the surface of Yellowstone, hidden far below the forests and rivers, lies a world that few ever imagine. It is not a single cavern of fire, but a layered system, a sleeping giant made of two immense magma chambers, stacked one above the other. The first rests closer to the surface, a shallower body of molten and semi-molten rock that stretches for miles beneath the caldera. Below it lies an even larger reservoir, a deeper chamber that reaches into the crust like a vast ocean of heat. Together, they form one of the largest volcanic systems ever discovered, a reminder that what appears as quiet land above is balanced on extraordinary forces below. The magma in these chambers is not uniform. It is not the smooth, glowing lava that flows from places like Hawaii. Instead, much of Yellowstone's magma is rhyolitic in composition, a form of molten rock that is thick, sticky, and volatile. Rhyolitic magma holds an immense amount of dissolved gases, and those gases are what make it so dangerous. As pressure builds, the magma resists release. When it finally breaks free, the gases explode outward with tremendous force, turning liquid fire into airborne ash and pulverized rock. This is why rhyolitic eruptions are among the most violent on Earth. They do not pour slowly across the ground, they tear landscapes apart in an instant. For centuries, this hidden world remained only a theory. People knew Yellowstone's surface was restless, with geysers erupting and hot springs steaming, but they could not see into the depths. That changed with the tools of modern science. Seismic waves from earthquakes began to reveal the outlines of chambers below. Each tremor that passed through the earth slowed slightly when it crossed molten zones, offering scientists a way to map the shape and scale of what lay beneath. Like sound echoing through a dark cavern, these seismic signals traced the boundaries of a colossal underground system. What they discovered was staggering. The upper magma chamber is enormous, stretching roughly 30 miles across and several miles deep. But beneath it, the lower chamber is even larger, a reservoir so vast it alone holds more molten rock than some of the biggest volcanoes in the world combined. The two chambers are connected, exchanging heat and material, feeding the surface features that attract millions of visitors each year. And yet, this exchange also reminds scientists of the system's potential, for it shows how the giant breathes, slowly and silently, beneath the crust. When scientists first calculated the total volume of molten material in Yellowstone, the numbers were almost difficult to believe. To put it in perspective, the energy stored in these magma chambers has been compared to thousands upon thousands of nuclear bombs. Unlike a weapon, it is not designed to destroy, but its natural capacity for release is of the same order of magnitude. It is energy written into the planet itself, waiting beneath the ground, capable of erupting not in seconds like a bomb, but over days and weeks, reshaping continents in the process. It is this scale that captures the imagination and unsettles the mind. Most volcanoes have small chambers, localized pockets that can erupt with devastating but contained consequences. Yellowstone is different. It is not a mountain that can be measured in simple height. It is a vast underground architecture, layered and connected, its full shape invisible to the eye, yet unmistakable in its seismic signature. Each earthquake, each pulse of the ground, reminds researchers that they are standing above a giant whose size is measured not in miles of height, but in miles of depth and width, spread across the heart of a continent. And still, the system is not static. Seismic imaging over the years has revealed movement within these chambers, subtle shifts in how magma rises and falls, how heat migrates, and how the earth flexes above it. The surface swells slightly in some decades and settles again in others, like the chest of a sleeping being drawing slow breaths. This restless motion is not yet eruption, but it is a sign of life, a reminder that Yellowstone is not a fossil or a relic of ancient fire. It is alive, its giant body hidden beneath soil and stone, but its presence as real as the mountains that surround it. As scientists continue to study this world beneath our feet, they refine their maps, sharpen their models, and listen more carefully to the giant's faint movements. What they see confirms both the power and the fragility of our place above it. For this is not just a reservoir of fire, it is the very engine that has shaped the land, sculpted the caldera, and left behind the surface wonders we see today. The story of Yellowstone is written in these hidden chambers, the unseen architecture of molten stone and gas. To walk its forests or watch its geysers is to tread above an underground giant, still breathing, still waiting. And it is in the memory of past eruptions that we begin to understand just how much change this giant has already unleashed and what it could yet do again. The ground beneath Yellowstone has not always been silent. Its past is marked by eruptions so vast that they left scars across an entire continent. Scientists trace this history not through stories told by people, for humanity did not yet exist when these events unfolded, but through the layers of rock and ash that still blanket the land. The first of Yellowstone's great eruptions took place around 2,100,000 years ago. It was an eruption of such magnitude that it emptied much of the magma chamber beneath the Earth's crust, collapsing the surface above and creating the earliest caldera in what is now Yellowstone. The ash from this eruption spread across North America, settling into layers that can still be found in the soils of distant states. Tiny crystals within the ash carry a chemical fingerprint, allowing scientists to match them back to this single eruption, proving that one event reshaped thousands of miles of landscape in only a matter of days. The second great eruption came roughly 1,300,000 years ago. Though smaller than the first, it was still one of the most violent events in Earth's recent geological past. Ash from this eruption fell over much of the continent, thickening soils in some areas by several feet. Rivers were clogged, valleys were filled, and the air itself would have been darkened for weeks. The land where the eruption began caved in once again, leaving behind a caldera within a caldera, a reminder that Yellowstone's system was far from exhausted. The most recent of these colossal events happened around 640,000 years ago. This eruption is the one most people think of when they imagine Yellowstone's destructive power. It was vast enough to cover more than half of what is now the United States in a layer of ash. To the west, the ash beds in places like Idaho and Nevada are still so thick and widespread that they form entire geologic units, preserved like pages of a book. To the east, fine particles drifted on the winds, dusting lands as far as the Gulf of Mexico. Even now, scientists uncover these layers during field work, measuring their depth and mapping their spread, building a picture of the true scale of the event. When these eruptions are compared to more recent volcanic disasters, their size becomes even clearer. The eruption of Mount St. Helens in 1980 was one of the most famous volcanic events of the modern era, yet it is considered tiny next to Yellowstone's history. The ash released by St. Helens could fit inside only a fraction of Yellowstone's ancient blasts. Krakatoa, which erupted in 1883 and created sunsets so vivid that they were recorded in paintings around the world, also pales in comparison. The force of Yellowstone's supereruptions was hundreds to thousands of times greater, a reminder that we are dealing with something on a scale that defies normal human experience. These eruptions left behind scars that remain visible in Yellowstone today. The caldera, stretching for more than 40 miles across, is one of the largest features in the park, though its true outline is difficult to see from the ground. Mountains were leveled, valleys filled, and rivers redirected. The landscape that millions of visitors now hike through, with its forests and lakes, is a surface shaped not just by glaciers or erosion, but by the memory of fire. Even the great Yellowstone Lake, calm and shimmering beneath the mountains, rests partly within the collapsed basin left behind by the last supereruption. Beyond Yellowstone itself, the evidence continues. Geologists traveling across the continent encounter layers of volcanic ash buried in sediments, each one a marker of Yellowstone's reach. In Nebraska, Kansas, and Oklahoma, farmers plowing their fields sometimes unearth fine layers of volcanic glass, remnants of eruptions that occurred long before people walked the earth. These discoveries remind us that Yellowstone's story is not local, but continental. Its reach extends across the heartland, recorded in soils, lakes, and ancient sediments. This history written in ash is not just a record of destruction, it is also a record of how landscapes recover. Forests returned, lakes filled with water, wildlife adapted and spread, life found its way back to the surface, though always changed by the events that came before. What we see today, the geysers and hot springs that dot the park, are echoes of this past, whispers from the chambers below that still breathe with heat. The scale of Yellowstone's eruptions is difficult to comprehend, but the evidence is all around. Every layer of ash, every scar in the land, every caldera within a caldera is a reminder that the ground beneath Yellowstone has not always been quiet. And as scientists look back on these immense events, they also look forward, knowing that the past is the key to understanding what may one day come again. To understand Yellowstone today is to look not only at what it has done in the past, but at how it behaves in the present. Scientists know that the supervolcano will erupt again one day, but the timing remains hidden. It may be thousands of years away, or it could stir sooner than anyone expects. Because of this uncertainty, Yellowstone is watched more closely than almost any other place on Earth. Its surface beauty draws millions of visitors each year, but beneath that beauty lies a system so immense that it demands constant attention. Each day, a network of instruments scattered across the park listens and measures. Seismographs are placed like ears pressed to the ground, recording even the smallest tremors that ripple through the crust. Most of the time, these movements are minor, nothing more than the restless shifting of a giant that continues to breathe in its sleep. Yet at times, the calm gives way to swarms of earthquakes, clusters of small quakes that can number in the hundreds over just a few weeks. To those who live nearby, these swarms often pass unnoticed, but to volcanologists, they are crucial clues. They reveal magma or hot water shifting beneath the surface, moving through fractures and cracks. These swarms are not signs of imminent eruption on their own, but they are part of a story that scientists piece together day by day. The ground itself also moves. Instruments using satellites and GPS measure the rise and fall of Yellowstone's floor, with precision measured in millimeters. Over the years, entire sections of land have swelled upward, lifted as though something below were pushing gently against the surface. At other times, the land has slowly subsided, sinking back as the system relaxes. These motions are too gradual for the eye to see, but when scientists compare data over years and decades, they map the slow breathing of the caldera. Each rise hints at magma or fluids pressing upward. Each fall suggests a release of pressure. Together, they show that Yellowstone is not a fossil of ancient fire, but a living system, always in motion. Even the geysers and hot springs are part of this monitoring. Old Faithful, with its familiar eruptions, has been watched for more than a century. When its timing shifts, even by minutes, researchers take notice. The patterns of geysers are linked to the plumbing of the system beneath. When water pathways change or new fractures open, geysers may erupt more frequently, or they may fall silent altogether. Other features, like Steamboat Geyser, the tallest in the world, sometimes remain quiet for years before suddenly springing to life with towering bursts of steam and boiling water. These unpredictable changes become part of the broader puzzle, showing how heat and pressure are moving through the park. The gases escaping from the Earth are another vital piece of evidence. Carbon dioxide, sulfur dioxide, and other volcanic gases rise invisibly from vents, pools, and fumaroles. Special instruments measure their quantity and composition, because changes in gas emissions can reveal what is happening deep below. A sudden increase in sulfur dioxide, for example, may indicate magma rising closer to the surface. The smell of sulfur that visitors sometimes notice near hot springs is not only a curiosity, but a constant whisper from the chambers below, a chemical signal of activity within. Together, these systems of monitoring form the only early warning tools we have. Yellowstone cannot be stopped or deflected. Its power is too great, its processes too deep, but by listening carefully to the ground, measuring its motions, studying its geysers, and sampling its gases, scientists can look for signs of change. If the system were ever to shift toward eruption, these would be the signals to reveal it. An increase in earthquake swarms, Rapid uplift of the land, unusual gas emissions, and changes in geyser activity would together suggest that something larger might be on the horizon. The task is one of patience and vigilance. Most days, Yellowstone is calm, its signals steady and familiar, but the data still matters because it builds a baseline, a record of what normal looks like. Without this constant watch, any future changes could go unnoticed until it was too late. This is why the Yellowstone Volcano Observatory, a collaboration of scientists from across the United States, dedicates itself to the daily task of listening. Every tremor, every shift, every plume of gas is logged and studied, contributing to a deeper understanding of the monster that sleeps beneath the park. What this vigilance tells us is not only about Yellowstone itself, but about how humanity relates to forces larger than civilization. Here is a system beyond our control, yet not beyond our ability to observe. By watching carefully, scientists hope to recognize the earliest signs of awakening. That recognition might provide days, weeks, or even months of warning, enough time to save lives and prepare for what could come. It is not prevention, but it is the only defense we have. And as this watch continues, the memory of Yellowstone's past eruptions remains in the minds of those who study it. The scars left on the continent, the ash beds still found across distant states, and the vast caldera itself are reminders of what this volcano has done before. With every passing year of monitoring, scientists are not simply waiting for disaster, they are learning how a giant lives, breathes, and changes beneath our feet, building knowledge that might one day make the difference between surprise and survival. When scientists speak of the dangers that could reshape life on Earth, two images often arise. One is the vision of a great rock falling from the sky, an asteroid blazing through the atmosphere, striking with the power of 1,000 weapons of war. The other is quieter, hidden beneath the crust, a supervolcano whose eruption would not begin with fire in the heavens, but with the ground splitting open at our feet. Both are capable of altering the course of history, yet when scientists weigh them side by side, many admit they fear Yellowstone more than asteroids. To understand why, it helps to look first at the scale of asteroid impacts. 66 million years ago, at the end of the Cretaceous period, a rock known as the Chicxulub impactor fell from space. It struck the Yucatan Peninsula in what is now Mexico, creating a crater more than 100 miles wide. The energy released in that single moment was equal to billions of nuclear bombs detonating together. Within hours, shock waves pulsed through the oceans, tsunamis rose higher than skyscrapers, and wildfires ignited across continents. Dust and sulfur filled the skies, blocking out the sun and collapsing food chains. The dinosaurs, rulers of the earth for more than 150 million years, vanished in the aftermath of this single event. It is the most famous example of cosmic violence, a reminder that the Earth's story has been shaped by forces from beyond our world. But Yellowstone carries a different kind of power. Unlike an asteroid that must strike by chance, Yellowstone is already here. It is not waiting in the void of space, but slumbering in silence below our feet. A supereruption from this caldera could eject thousands of cubic kilometers of ash into the atmosphere, a quantity so vast that it is difficult to imagine. The ash would not remain near the park's borders. Winds would carry it across the continent, darkening skies, collapsing buildings beneath its weight, and suffocating crops and rivers. Electrical grids would fail as ash choked machines. Water systems would be poisoned by the fine volcanic dust. The effects would not end with ash. Once gases like sulfur dioxide were lofted high into the stratosphere, sunlight itself would be dimmed. Temperatures across the planet would plummet, not just for weeks or months, but for years. Crops would wither in fields, harvests would fail season after season, and billions of people would face famine. Scientists call this scenario a volcanic winter, a time when the earth shivers under its own breath, when the climate is shifted by fire, not from the heavens, but from deep inside the earth. Part of what makes Yellowstone even more unsettling than an asteroid is probability. Asteroids the size of Chicxulub are rare. They strike only once every tens of millions of years. Smaller asteroids, though more common, are far less destructive, and humanity has already begun to track them. Telescopes scan the skies, cataloging objects that pass near Earth. Space agencies are testing technologies to deflect or disrupt them, pushing us toward a future where the threat of a planet killer from space may be reduced. Yellowstone is different. Supereruptions here have taken place every few 100,000 years. The last occurred around 640,000 years ago. This does not mean another is overdue, but it does mean another will eventually come. Unlike asteroids that can be nudged away with human engineering, a supervolcano cannot be stopped. Its forces are written into the crust of the Earth. No barrier or technology can deflect it. It is a hazard that lives within the planet itself, silent and patient. The contrast becomes even sharper when looking at timescales of impact. An asteroid is sudden, almost cinematic. It arrives in a blaze, striking the Earth in a matter of seconds, and the destruction is immediate. Yellowstone, by comparison, unfolds like a slow, creeping nightmare. It would begin with earthquakes swarming through the park, a collapse of the ground, and great plumes of ash climbing into the sky. The eruption itself could last for days or weeks, but the consequences would linger far longer. The fallout of ash would spread in waves, the cooling of the climate would stretch over years, and the collapse of food systems could echo for decades. Where an asteroid is a fireball of extinction in a single day, Yellowstone is an unraveling of climate and civilization stretched across time. This is why scientists, when asked which they fear more, often point to Yellowstone. We can see asteroids coming. We can watch their orbits and track their approach years or decades in advance. We can attempt to build strategies to push them aside. Yellowstone does not offer this clarity. It hides in silence. Its signals are subtle, whispers in the form of earthquakes or gas emissions, changes in geysers, or the slow uplift of the ground. And even when those signals are detected, they do not tell us when the eruption will come, only that the giant still breathes. One threat comes from beyond the sky, rare and improbable, yet visible and perhaps deflectable. The other comes from within, inevitable on the scale of geologic time and impossible to stop. Both would be devastating, but Yellowstone carries a weight of certainty. The Earth will one day produce another super eruption. Whether it happens in our lifetime or 10,000 years from now, it is a question of when, not if. This is why volcanologists place Yellowstone among the greatest threats to life as we know it, not because it is likely to erupt tomorrow, but because when it does, the entire world will feel its shadow. If Yellowstone were to awaken tomorrow, the first signs would not be the towering plumes of ash or fire, but the trembling of the ground itself. In the hours leading up to eruption, earthquake swarms would ripple through the park, hundreds and then thousands of small quakes, each one a signal of magma forcing its way upward. Visitors might first notice a subtle vibration underfoot, or the rattling of windows in cabins and lodges. Soon, the swarms would intensify, too rapid to count, shaking the land with an unrelenting rhythm. Seismographs would record them as a blur of jagged lines, warning that the giant beneath was no longer resting quietly. The ground would begin to change in ways both strange and frightening. Roads would crack as the earth lifted unevenly. Hillsides might slump and collapse as pressure forced its way toward the surface. Geysers, once predictable in their eruptions, would behave erratically, some falling silent while others roared to life in bursts of steam and boiling water. These signals would give only hours of notice, for once the caldera roof begins to fail, The rest follows quickly. At the heart of Yellowstone lies a vast chamber of magma, pressing upward against the brittle crust. When the pressure finally exceeded the strength of the rock, the roof of the caldera would collapse, and imagine an area larger than entire cities sinking in on itself, creating a violent chain reaction. The collapse would release the pressure suddenly, like uncorking a bottle of trapped gas, and the eruption would begin. In minutes, fountains of molten rock and fire would tower into the sky, some reaching heights measured in tens of thousands of feet. The eruption column would form with terrifying speed, a rising pillar of incandescent ash and glowing fragments that raced into the upper atmosphere. The light of day would be swallowed by the sheer density of the plume. For those within sight, it would appear as if the sky itself had opened and was pouring fire onto the earth. Ground Zero, the area surrounding the caldera, would be consumed almost instantly. Everything within dozens of miles would be vaporized or buried in pyroclastic flows, avalanches of ash, gas, and rock moving faster than a jet plane. These flows would flatten forests, scour the land, and leave behind a barren, lifeless plain. Towns and communities in the immediate path would disappear in moments, erased as though they had never existed. Farther away, the destruction would take a different form. Ash would begin to fall within minutes, at first as a fine dust drifting quietly from the sky, then as thick layers that coated every surface. Cars would stall as engines clogged, power lines would sag under the weight, and rivers would turn gray with the flood of ash. For people hundreds of miles away, it would feel like a blizzard of stone dust, a suffocating storm that offered no escape. The fine particles, sharp as glass under a microscope, would invade lungs and water supplies, making survival increasingly difficult even outside the immediate blast zone. The noise of the eruption would echo across the continent. Explosions from within the caldera would be heard for thousands of miles, like rolling thunder without end. Shock waves would travel through the atmosphere, rattling windows and shaking buildings far beyond the park. The sound alone would be a reminder that this was no ordinary eruption, but one of the largest natural events possible on Earth. Meanwhile, in the sky above, the ash plume would continue to grow. Within an hour, it could stretch higher than commercial airplanes fly, spreading outward in vast mushroom-like shapes. Lightning would crackle within the plume, born from the collision of ash particles, painting the darkened sky with flashes of electric fire. The combination of lightning, boiling ash, and glowing magma would create a scene unlike anything in living memory, a reminder of how small humanity is in the face of geologic power. At ground zero, life would already be over. Trees, rivers, and animals would vanish under walls of burning debris. In the wider region, cities would struggle to comprehend what was happening as ash fell thick and fast. Flights would be grounded immediately, communications would falter, and roads would clog with those desperate to flee. Yet escape from ashfall would be nearly impossible, as winds carried the cloud in all directions. All of this would happen within the first hours of the eruption, not days, not weeks, but in the time it takes for the sunlight to cross a single slice of the sky. The first stage of Yellowstone's awakening would already have rewritten the land around it, creating a scene both apocalyptic and awe-inspiring. And yet, this would only be the beginning, for the ash would not stay in one place, and the darkness would soon spread across the entire continent. When the first fountains of fire and ash had finished clawing their way into the sky, the true weight of Yellowstone's eruption would begin to reveal itself, not in a single explosion, but in the quiet, steady descent of ash. Unlike ordinary dust or the soft flakes of snow, volcanic ash is something else entirely. It is made of pulverized rock, shards of glass, and tiny crystals, shattered by unimaginable heat and carried upward on violent columns of air. Each grain is sharp and heavy, so fine that it drifts for miles, yet dense enough to settle with the weight of stone dust. And when it begins to fall, it does not stop. The winds that sweep across North America would carry the ash far beyond the borders of Wyoming. At first, it would be a haze, a gray veil softening the horizon, but soon the particles would thicken into a storm that coated everything it touched. Fields of wheat and corn would vanish under a powder that no plow could turn. Rivers would turn black, their surfaces choked with drifting mats of volcanic debris. The roofs of homes would creak and groan under the growing burden until they collapsed altogether, folding inward beneath the weight of what looked from a distance like harmless dust, but was in truth as heavy as stone. Cities would find themselves smothered in layers that deepened with every passing hour. Roads would become impassable as ash piled ankle deep, then knee deep, clinging to shoes and clogging engines. Cars left running would stall, their air filters clogged by the razor-edged fragments. Power stations would falter as transmission lines sagged and broke beneath the mounting load. Even the simple act of breathing would turn dangerous. Unlike ordinary smoke, volcanic ash slices the lungs with each breath. Its microscopic shards can scar tissue, leading to suffocation in both people and animals. Emergency rooms would overflow with those struggling for air, their throats raw, their eyes burning. For animals grazing in the open, survival would be no easier. Cattle would collapse in fields as their food vanished beneath layers of ash. Rivers and watering holes would become toxic slurries, the water fouled by dissolved chemicals. Birds would fall from the air, their wings coated, and weighed down until flight became impossible. Even wild herds, strong and untamed, would face a new world where every blade of grass was buried, every breath filled with poison. The ash would not fall evenly. Maps produced by scientists long before any eruption show the patterns of prevailing winds, spreading the cloud eastward and southward across the United States. Within a few dozen miles of Yellowstone, ash could pile meters deep, burying the land as thoroughly as a glacier. Hundreds of miles away, the layers would thin, but even a few centimeters would be enough to paralyze daily life. States like Colorado, Nebraska, and the Dakotas could find themselves buried beneath a blanket of gray, their skies darkened, their air thick with choking grit. The Midwest, America's breadbasket, would lie directly in the path of destruction. Fields that once produced endless harvests of grain would be rendered useless, their soil sealed off by a crust of volcanic glass that no seed could pierce. Even on the coasts, thousands of kilometers from the eruption, a fine dusting would still arrive. Planes would be grounded across the nation, their engines unable to function in the abrasive air. Solar panels would be darkened, water treatment plants clogged, and entire regions cut off from electricity and clean drinking water. The fall of ash would not be a passing event, but a constant, lasting days and then weeks, settling out in layer after layer until much of the continent lay hidden beneath a shroud of gray. The map of fallout zones would be a portrait of silence and paralysis. At its heart, Wyoming and the neighboring states would be unrecognizable, buried beneath meters of choking debris. Surrounding them, a vast oval stretching across the Midwest would lie under half a meter or more than enough to collapse infrastructure and suffocate crops. Beyond that, a wider zone covering nearly the entire United States would still find itself blanketed in centimeters, enough to poison water, stop engines, and contaminate every lung. Scientists have modeled these scenarios again and again, and though the exact shape may depend on the winds, the story remains the same. No corner of the nation would be untouched. The ash would not simply fall and stay still. Every gust of wind would raise clouds of it back into the air, a constant storm of particles that refused to settle. Cleanup would be nearly impossible. Attempts to clear roads or rooftops would only stir the dust back into the atmosphere, where it would drift into lungs and eyes once again. The entire continent would become a landscape reshaped, not just by fire and explosions, but by the slow, relentless weight of ash falling out of the sky. And all of this would only be the beginning, because once the land was buried, the skies would begin to darken in ways the modern world has never known. As the ash continued to spread across the land, it would not remain only at the surface. Carried upward by the violent force of the eruption, countless particles would drift into the highest reaches of the atmosphere, where winds would scatter them far beyond the continent. Alongside the ash would come vast amounts of sulfur dioxide and other gases, rising higher still, spreading thin veils of aerosols across the stratosphere. There, suspended above the world, these microscopic droplets and particles would perform their slow, inexorable work. They would bend and scatter sunlight, turning the brilliance of day into something dim and muted, like the light of evening stretched across the hours. The world would not go completely dark. The sun would still rise, but its face would be hidden behind a shroud. Days that once began with golden light would unfold under a sky the color of ash. Noon would feel like twilight, and the horizon would blur into shades of gray. Even far from Yellowstone, thousands of kilometers away, the sunlight would weaken, filtered through layers of drifting debris. Crops would struggle under skies that no longer gave enough energy. Solar panels would produce only a fraction of their normal power. People everywhere would look upward and realize the world had changed. Yet in the midst of this muted daylight, evenings would take on a strange, haunting beauty. As the sun dipped low, its rays would pass through thick layers of ash and aerosols, scattering into deep hues of crimson and orange. Fire-red sunsets would stretch across continents, painting the sky in colors so vivid they would seem almost unreal. From Africa to Asia, from the Americas to the far islands of the Pacific, the heavens would glow with a light that was both mesmerizing and unsettling. For some, it would inspire awe. For others, it would serve as a daily reminder that the air itself carried the mark of disaster. The beauty of these sunsets would be brief comfort, for with the lengthening twilight would come the deepening of night. As the particles spread and thickened, even starlight would be muted, and the moon would glow pale and indistinct, its light diminished by the haze. The world that once seemed familiar in its daily rhythms of day and night would feel altered, as if Earth itself had slipped into a different age. The toll on the human mind would be subtle at first, then heavy. For all of history, people have risen with the sun, marking time by the turning of day into night. With that cycle disrupted, the sense of order that anchors human life would begin to waver. Months of dim skies would blur into one another, and the absence of true daylight would weigh on entire populations. Studies of volcanic eruptions in the past, such as Tambora's eruption 2 centuries ago, reveal how the dimming of the skies left communities with feelings of dread, despair, and confusion. Now imagine those effects multiplied across every continent. Children would grow restless under skies that never brightened. Farmers would struggle to predict planting or harvest times when the sun gave no steady guidance. Even in cities where artificial light kept streets glowing, the lack of natural sunlight would sap energy and mood. The very sight of the horizon would feel foreign, as if Earth had been cloaked in a veil of mourning. And as this twilight world continued, the consequences would extend beyond emotion. Reduced sunlight would mean colder days. The atmosphere, shaded by its blanket of aerosols, would begin to cool. Seasons would falter, summers turning cold, and winters becoming harsher still. The darkened skies would be more than a spectacle, more than a psychological burden. They would be the harbinger of a world shifting into volcanic winter, a slow motion catastrophe unfolding with each passing day. From the first falling ash to the fire red sunsets and the muted noons, the darkening of the sky would not just be an atmospheric change, it would be a reminder that the Earth itself had entered a different chapter, one written in gray light and crimson horizons, with consequences that would reach far into every field, every home, and every heart. When the skies dimmed and sunlight no longer poured freely to the Earth's surface, the next stage of Yellowstone's awakening would quietly begin. The air itself, once warmed by the sun's rays, would start to cool. The ash and aerosols drifting high in the stratosphere would reflect sunlight back into space, acting like a veil stretched across the planet. The result would be a sudden drop in temperatures, felt not just in the shadow of Yellowstone, but across the entire globe. In the first weeks, the change would be subtle. Mornings would arrive with a sharper chill, and days that should have been warm would feel more like early spring. As months passed, the decline would grow unmistakable. Average temperatures across continents would sink by several degrees. At first, this might sound small, but Earth's climate is delicate, and even a few degrees can mean the difference between fertile summers and barren fields. Soon, the phrase years without summer would no longer belong only to history. It would become reality once more. During the eruption of Tambora in the early 19th century, a single volcano in Indonesia sent enough ash into the skies to darken the sun and cool the world. In the aftermath, 1816 became known as the year without a summer. Frost fell on crops in June, snow blanketed fields in July, and harvests failed across Europe and North America. Now imagine that same scenario, magnified many times over, spreading for years, not just one. That is the scale scientists expect from a Yellowstone supereruption. Fields that once swayed with golden wheat would lie barren, their seeds unable to grow under cold and dim skies. Corn, rice, and soy, staples that billions depend upon, would wither before they matured. Farmers would watch as plants struggled in soil that remained cold, their growth stunted by the lack of sunlight. In many regions, harvests would not simply be poor, they would vanish entirely. This collapse of agriculture would strike modern society with a force few could anticipate. We live in an age where global food systems are finely tuned and deeply interconnected. Grain from the American Midwest feeds nations across the world, while rice from Asia and maize from South America sustain continents far beyond their borders. When those harvests fail, there is little margin left. In ancient times, people endured famine by retreating into smaller local food systems, but today, billions rely on a global chain, one that would shatter if the fields went empty. The pressure on food reserves would mount within months. Shelves in grocery stores would empty as supplies dwindled. Prices would soar beyond the reach of ordinary families. Nations that depended on imports would find themselves desperate for trade that no longer existed. Governments would attempt to ration, but even with strict control, the sheer scale of need would overwhelm supply. And beneath the surface of these practical struggles lies something older and more haunting. For the first time in centuries, modern humanity would be thrust into struggles our ancestors knew all too well. The search for warmth, for food, for survival through long cold seasons. It would not matter that the cause was invisible particles floating high above, or that satellites and sensors tracked every shift in temperature. The reality on the ground would be ancient in its essence, a battle against hunger and cold that humanity has fought again and again. Livestock would suffer alongside people, with pasture buried under ash and grain supplies exhausted. Herds would shrink rapidly. Milk and meat would disappear from diets. The ocean, too, would feel the burden. Cooler waters and disrupted currents would reduce fish stocks, depriving billions of one of their most vital sources of protein. The abundance of the modern world, once taken for granted, would fade into scarcity. Each season would bring new reminders of the altered climate. Springs would arrive late, if at all. Summers would be brief and muted, marked by stunted growth and endless gray skies. Autumns would descend into frost far too early, and winters would bite with unusual severity. The rhythm of life, measured for thousands of years by the dependable turn of seasons, would be broken, and with each passing year, the question would linger: how long would the volcanic winter last? Some climate models suggest that cooling could grip the Earth for a decade or more before the skies began to clear. Others warn that recovery could take far longer, depending on how much sulfur dioxide the eruption injected into the stratosphere. For those living through it, the timescale would hardly matter. Each day without warmth, each failed harvest, each empty storehouse would bring the same reality into sharper focus. The beginning of volcanic winter would not be marked by a single event, but by a slow, inexorable shift. A chill in the air, a failed harvest, a season that refused to come. It would be as if the world had turned a page, entering a new chapter written not in growth and abundance, but in shadows and scarcity. And from there, the consequences would deepen as societies confronted the collapse of food itself. As the volcanic winter deepened, its shadow would reach into the very heart of human survival: food. For all the ingenuity and technology of the modern age, our civilization rests on a fragile foundation. The vast networks that carry grain, vegetables, and meat across oceans and continents appear strong, but they are held together by a delicate balance of climate, soil, and sunlight. When Yellowstone darkens the sky and chills the air, that balance begins to break. In the earliest months, it would be the farmers who noticed first. Crops that should have stretched tall in the summer sunlight would wither in cold fields, their leaves stunted and pale. The soil itself would feel different, too damp or too dry, no longer following familiar seasonal rhythms. Machinery and fertilizers could not change what the sky refused to give. Yields would shrink and then vanish altogether until entire harvests failed across wide regions of the world. The collapse of local harvests would ripple outward. In a globalized system where nations depend on one another for staple foods, the shock would move quickly. Countries that once exported grain would hold it back, keeping what little they had for their own people. Ships that usually crossed the oceans heavy with cargo would sit idle, their holds empty. Markets would feel the shift almost instantly, with prices of wheat, rice, and corn spiking higher than ever before. Families already living close to the edge would find themselves unable to afford even the simplest meals. Soon, the crisis would grow larger than any one country. Billions of people rely daily on the steady flow of food through this web of trade. When that flow halts, the numbers at risk of famine would be staggering. Children would grow thin first, their bodies unable to withstand the lack of nourishment. Entire regions, especially those most dependent on imports, would face hunger on a scale not seen in modern history. The echoes of the past would suddenly feel very near. In the year 1816, when the eruption of Tambora dimmed the skies, farmers across Europe and North America faced snow in midsummer, frosts that destroyed crops, and rains that never ceased. Grain prices soared, livestock perished, and countless families went hungry. It was a single volcano, yet it was enough to create misery across much of the northern hemisphere. The memory of that year, without a summer, has been preserved in diaries, paintings, and historical records, but it would pale in comparison to what Yellowstone could bring. Modern climate models attempt to capture what such an eruption would mean. They suggest that the cooling from a Yellowstone supereruption could last for a decade or more, with the worst years bringing harvest failures across multiple continents at once. In such conditions, reserves would be quickly exhausted. Even the grain stored for emergencies, meant to last a year or two, would vanish far too soon. Nations that once prided themselves on self-sufficiency would find that no vault was deep enough, no storage broad enough to outlast the skies. Famine would not strike in the same way everywhere. In wealthier regions, shortages might first be felt as empty supermarket shelves, or as prices rising beyond imagination. In poorer countries, it would be immediate and brutal, as food disappeared altogether. Hunger would spread unevenly, but it would spread nonetheless, moving like a tide that no border could hold back. The human cost would be measured not only in empty stomachs, but in the unraveling of societies. Families would abandon their homes in search of food, swelling refugee numbers in places already under strain. Governments would struggle to maintain order as desperation turned into unrest. And even in places not yet touched by famine, fear of what might come would gnaw at daily life, making scarcity feel like a universal shadow. Scientists who study such scenarios try to model how long the famine might last, but the answers depend on many unknowns. How much sulfur dioxide would be released into the stratosphere? How far would the ash and aerosols spread? How many summers would vanish before the earth began to heal? Some estimates suggest a decade of serious disruption, others warn of longer. What is certain is that even a handful of years without stable harvests would be enough to push billions into hunger, reshaping human life in ways difficult to fully imagine. The collapse of food would not be a single event, but a slow and relentless decline, rippling outward from fields that no longer grew, to markets that no longer traded, to homes where meals grew smaller and finally disappeared. And as plates emptied across the world, the consequences would touch every corner of society, pressing into the very systems that keep our lives ordered and connected. From there, the strain would begin to crack more than just the food chain. It would spread into the networks of power, transport, and communication that sustain modern civilization, leading into the next stage of Yellowstone's story. When food began to vanish and hunger spread across nations, another kind of collapse would follow, one less visible at first but just as paralyzing. It would start with the systems that connect the world, the networks of power, travel, and water that modern life depends on. These structures are strong, yet they are fragile in the face of ash. The sky would become a barrier long before the ground did. Volcanic ash is not like the fine dust that sometimes settles on windshields. It is sharp and heavy, filled with glassy fragments that grind and cut. For aircraft, it is deadly. Engines that inhaled even a small amount would clog and stall, their blades eroded by microscopic shards. In the first hours of the eruption, flights across the western United States would be grounded, but as the ash cloud spread, airports across the continent would close. Then the shutdown would ripple outward until international air travel ceased altogether. Skies that once carried thousands of planes each day would empty, leaving nations cut off from one another. The ground would fare no better. Power grids, the veins of electricity that run across landscapes, would buckle under the weight of ash. Transmission lines would sag as the particles piled on, their metallic surfaces coated with the abrasive dust. Substations and transformers would clog and short-circuit when the ash became wet, mixing with rain or snow to form a cement-like paste. Across vast regions, the glow of electric light would fade, plunging cities into darkness. The silence of powerless streets would spread like another kind of shadow, one that reached into every home. Water, too, would no longer be safe. Volcanic ash carries toxic elements, and as it washed into rivers, reservoirs, and lakes, it would poison supplies. Water treatment plants would struggle as filters clogged with grit, unable to keep up with the flood of contamination. Entire towns might turn on their taps only to find murky liquid flowing out, unsafe to drink, unsafe even to use for crops. Bottled reserves would vanish quickly, leaving communities desperate for clean sources. In the countryside, wells and streams would offer no refuge, for the ash would seep into groundwater as well. These failures would not happen separately, but all at once. The fall of ash would touch every system, unraveling them in a tangled web. Without planes, trade would falter. Without power, communication networks would collapse, silencing phones and the internet. Without water, sanitation would break down, disease would spread, and people would turn to desperate measures to survive. And when systems failed, the weight of order itself would be tested. Governments and emergency services would be stretched far beyond their capacity. Police, firefighters, and hospitals would all face shortages, not only of supplies, but of energy and transportation. Roads would clog with stranded vehicles, their engines suffocated by ash. Deliveries of medicine and food would halt. In the confusion, fear and frustration would rise. Communities would try to hold together, but the pressure would grow immense. In some places, neighbors would share resources, banding together to endure the crisis. In others, desperation might spill over into unrest, as people struggled to claim what little remained. The thin line that separates stability from chaos would be tested everywhere. The picture is not only of broken machines, but of broken rhythms. A world that once hummed with constant motion would slow to a crawl. Airplanes grounded, streets silent, lights extinguished, water unsafe, and people waiting in lines that stretched for blocks, hoping for aid that might never arrive. For all the progress of modern civilization, Yellowstone's ash would remind humanity that its strength is built on systems that can falter in an instant. And as these networks collapsed, the effects would not remain confined to one country or even one continent. The failure of trade, energy, and clean water would echo through global markets and economies, setting in motion the next chain of consequences. When the ash muted the skies and food became scarce, the world's intricate web of trade and finance would begin to unravel. Modern economies depend on constant motion, ships sailing across oceans, trucks moving across borders, planes lifting off every hour. But when fields no longer yield their harvests, when planes are grounded, and when markets realize that supply lines have fractured, panic spreads faster than the ash itself. The first signs would be seen in the markets, where confidence is as fragile as glass. Prices for staples like wheat, rice, and corn would soar, climbing higher with each passing day as scarcity became undeniable. Investors, once calm, would race to withdraw, creating a cascade of sell-offs that pushed stock markets into freefall. The numbers on financial boards would tumble downward, and with them the stability of economies across continents. The shockwaves of collapse would not be confined to agriculture alone, for when food falters, every other sector trembles. Trade would slow and then collapse entirely. Cargo ships that once carried grains across the seas would sit anchored in empty ports. The vast containers that once bustled with goods would gather dust. Nations that depended on imports for survival would face stark realities as the flow of goods that kept their populations alive was cut off. Exporting nations, meanwhile, would hold back what they had, their own people demanding that resources stay within their borders. What once bound the world together in a net of cooperation would begin to unravel strand by strand. The collapse of trade would ripple into industries far removed from the fields. Factories would close as supplies of raw materials dried up. Energy markets, already strained by power grid failures, would lurch into crisis. Tourism, transport, and technology would shrink to shadows of themselves. Millions would lose their jobs, and entire economies would shrink under the combined weight of scarcity and instability. The age of globalization, which once promised resilience, would be revealed as brittle when tested by the scale of Yellowstone's shadow. As famine deepened, migration would begin. Families with nothing left in their towns and villages would move in search of food and safety. Highways would fill with caravans of people on foot, in overloaded vehicles, or huddled together in makeshift transports. Borders would strain under the pressure of desperate waves. Wealthier nations, themselves reeling, would struggle to decide whether to close their gates or attempt to absorb the flood. Camps would rise where once there were open plains, and entire populations would shift across the earth in a search not for wealth, but for survival. The human tide would create tensions that rippled into every aspect of society. Countries already weakened by economic collapse would strain under new mouths to feed, while others would turn inward, clinging to their resources. The map of the world would begin to change, not with the strokes of politics, but with the footsteps of millions moving across landscapes darkened by ash. The pattern would not be new. History holds echoes of these same cascades. When Tambora erupted in the year 1815, the failure of harvests created depressions that rippled across Europe. Markets fell, food riots broke out, and migration surged as families fled the land. Even in North America, far from the volcano, farmers abandoned fields and sought better fortunes elsewhere. That event was born of a single eruption, smaller than Yellowstone, and yet it reshaped nations. Now, magnify those historical echoes across a globalized planet of billions. The dominoes would not fall in isolation, they would tumble into one another endlessly, markets into trade, trade into famine, famine into migration, migration into political and social upheaval. Each collapse would amplify the next, until the entire structure of global society trembled under the weight. And yet, the story would not end there, for the scars left by the eruption would not only be economic. The earth itself has recorded tales of destruction in its deep history, and the shadows of past extinction events whisper of what happens when volcanic fury reshapes the course of life itself. Long before Yellowstone ever breathed its first plume of steam, Earth had already been marked by catastrophes that reshaped life itself. The rocks beneath our feet carry these memories, written in ash layers, buried fossils, and chemical scars that whisper of worlds lost. To imagine the scale of Yellowstone's fury, it helps to look back at these ancient events, the echoes of mass extinctions that forever altered the story of life. Over 250 million years ago, long before the age of dinosaurs, a chain of volcanic eruptions tore open the crust of the planet in what is now Siberia. This was not a single eruption, but a relentless outpouring of lava and gas that lasted for hundreds of thousands of years. Geologists call this vast region the Siberian Traps, named for the step-like cliffs of ancient basalt that still stretch across the land today. The eruptions released unimaginable volumes of carbon dioxide and sulfur, blanketing the skies and poisoning the air. Oceans warmed, then turned acidic, stripping away life. On land, forests withered, rivers dried, and animals vanished. By the time the earth quieted again, more than 90% of all species had been erased. It was the greatest extinction in history, remembered as the Great Dying, a moment when life itself came close to ending. The scale of the Siberian traps shows how volcanism, stretched over vast spans of time, can change the course of evolution. Yellowstone is not of that same style, for it erupts in singular, violent bursts rather than endless flows. Yet the lesson remains clear. When magma, ash, and gases escape in such magnitude, the balance of climate and ecosystems can shift so severely that life struggles to endure. 66 million years ago, a different kind of disaster struck. A mountain-sized rock from space hurtled into the shallow seas of what is now Mexico, releasing an energy equivalent to billions of nuclear bombs. The Chicxulub impact was sudden, cinematic in scale. In minutes, shock waves rippled around the globe, tsunamis surged across oceans, and the sky ignited in firestorms as debris rained back to Earth. Within hours, daylight dimmed beneath a canopy of dust and soot. The dinosaurs, rulers of the land for over 160 million years, faced their end. 3 out of every 4 species vanished in the years that followed. The asteroid's impact is often seen as a unique catastrophe, something separate from volcanic disasters. Yet scientists have noted unsettling parallels. Both events fill the sky with choking debris. Both poison the air with gases that shift climate. Both block out sunlight and plunge the Earth into long, dark winters. Yellowstone's fury would not strike in the sudden brilliance of a fireball, but its ash and gases could produce effects on a similar scale, spreading famine and collapse over years instead of days. This comparison has led some scientists to frame Yellowstone as a kind of terrestrial asteroid, not falling from the heavens, but rising from beneath our feet. The difference lies not in potential impact, but in origin. One comes from space, a rare visitor striking by chance. The other is part of the Earth itself, born of its restless mantle, inevitable in its cycles of eruption. The sobering truth is that life has faced such trials before, and survival was never guaranteed. Each extinction event carved away vast portions of the living world, reshaping what remained. After the Great Dying, it took millions of years for ecosystems to recover, and even then, they bore little resemblance to what came before. After the Chicxulub impact, it was not the dinosaurs that thrived, but small mammals and birds, creatures that seized opportunity in the aftermath of collapse. Looking at these parallels forces a difficult reflection. Humanity has built a world of astonishing complexity, but that world is no less vulnerable than the ecosystems that crumbled in the past. The same forces that reshaped ancient oceans and ended the reign of the dinosaurs still exist beneath us. The story of the Earth reminds us that power on this scale is not fiction, but memory etched in stone. And as these memories rise to the surface, Yellowstone's threat becomes part of a much older pattern, a reminder that the forces capable of ending eras are still alive today, waiting in silence until the cycle turns once more. The echoes of extinction events stretch back millions of years, but the Earth has offered us more recent warnings too. In the last few centuries, humanity has lived through volcanic eruptions that reshaped weather, darkened skies, and even altered the course of history. Though these eruptions were far smaller than what Yellowstone could unleash, their consequences reveal the fragility of the world we live in. In the year 1883, the island of Krakatoa in Indonesia tore itself apart. The eruption was so violent that over 2/3 of the island collapsed into the sea. The explosion was heard across continents, from Australia to Africa, and shock waves circled the globe multiple times. The skies filled with ash and gases that spread across the stratosphere, scattering sunlight and creating sunsets of such brilliance that painters tried in vain to capture their colors. The cooling that followed dropped global temperatures by over a degree, enough to disturb weather patterns worldwide. Crops failed in some regions, monsoons shifted, and communities thousands of kilometers away suffered from famine and disease. All of this came from a single volcanic island. Just over a century later, in 1991, another eruption shook the Philippines. Mount Pinatubo released a vast cloud of ash and sulfur dioxide, blasting it high into the stratosphere. Within days, satellites could see the spreading haze encircling the globe. The gases reflected sunlight back into space, lowering global temperatures by about half a degree for several years. Scientists who studied the eruption noted how quickly weather patterns shifted, with altered rainfall and colder winters across many regions. The event became one of the best documented cases of volcanic cooling in modern times, a reminder that even in the late 20th century, humanity remained vulnerable to the moods of the earth. But perhaps the most haunting example of volcanic power in human memory comes from the eruption of Tambora in 1815. Located in Indonesia, Tambora produced the largest eruption in recorded history. The blast was so immense that it injected vast amounts of ash and aerosols into the atmosphere, dimming the skies across the northern hemisphere. The following year, 1816, became infamous as the year without a summer. Snow fell in June in North America. Frost struck in July, destroying crops in Europe. The monsoon season in India failed, sparking famine and epidemics. Hunger spread across continents, and the global economy staggered under the weight of shortages. Literature and history still carry the marks of that year, from desperate diary entries to stories written under darkened skies. These eruptions reveal how even a single volcano can disrupt the planet. They cooled the earth by small but significant amounts, altered rainfall patterns, and brought chaos to societies that relied on steady climates and fertile fields. And yet, all of them combined would still pale in comparison to the scale of Yellowstone. Krakatoa, Pinatubo, and Tambora each produced consequences that lasted years, but their eruptions measured in tens of cubic kilometers of material. A Yellowstone supereruption would eject thousands of cubic kilometers, multiplying those effects not by a factor of 2 or 10, but by thousands. Imagine the cooling of Tambora stretched across decades instead of 1 year. Imagine the haze of Pinatubo multiplied until no part of the globe remained untouched. Imagine the sound of Krakatoa's explosion, but amplified by a chamber of magma stretching beneath an entire national park. Each of these events was devastating, but Yellowstone represents a scale that dwarfs even the greatest of them. By studying these more recent eruptions, scientists have gained glimpses into how volcanic aerosols alter climate, how ash cripples infrastructure, and how famine follows swiftly on the heels of failed harvests. The lessons are stark. If smaller eruptions could change the fate of nations, then Yellowstone carries the potential to alter the fate of civilization itself. And just as history recorded how skies dimmed after Krakatoa and how crops failed after Tambora, it is certain that Yellowstone would leave its own mark, not just in science, but in the very survival of those who lived through it. The memory of those smaller eruptions reminds us that what lies beneath Yellowstone is not merely a local hazard, but a global threat. From these warnings in recent centuries, the story turns back toward Yellowstone itself, for the scale of its eruption would not simply echo the past. It could set off new chains of reactions that ripple through the earth in ways still difficult to predict. The eruption of Yellowstone would not exist in isolation. The Earth is a connected system, its crust a vast mosaic of plates and fractures, each piece under pressure, each fault line carrying the memory of past movements. When one part of this puzzle shifts, others feel the strain. In the wake of a Yellowstone supereruption, scientists have long wondered whether its violence could set in motion events far beyond Wyoming, creating a chain reaction that reaches across the globe. The idea begins with stress transfer. When magma forces its way to the surface and the caldera collapses, immense amounts of pressure are suddenly released. The surrounding crust, stretched and bent by centuries of buildup, snaps into new positions. Seismic waves ripple outward in every direction, shaking mountain ranges, river valleys, and plains alike. The ground hundreds of kilometers away may tremble, not just from the eruption itself, but from these vast shifts of stress. Faults that were already close to slipping could be pushed over the edge, triggering earthquakes far beyond the eruption zone. This is not speculation alone. History gives hints of how one event can awaken others. The eruption of Mount Pinatubo in the Philippines in 1991 was followed by swarms of earthquakes on nearby faults. The eruption of Mount St. Helens in 1980 altered seismic activity in the Pacific Northwest for months afterward. Even distant earthquakes, like the Great Sumatra Quake of 2004, have been recorded nudging volcanoes half a world away, shaking magma chambers just enough to stir them into unrest. If such connections exist on smaller scales, the energy unleashed by Yellowstone could ripple through fault systems like a stone cast into a still pond. The Cascades to the west, home to Mount Rainier, Mount Hood, and Mount Shasta, sit along a tectonic margin already alive with activity. To the south, the Great San Andreas Fault grinds endlessly, storing energy for future ruptures. If Yellowstone erupted with the force of thousands of nuclear bombs, the redistribution of stress could, in theory, shift the balance on these systems. It would not necessarily guarantee new eruptions or quakes, but the possibility lingers, a reminder of how interwoven Earth systems truly are. Beyond local effects, there is the larger question of global volcanism. Some scientists have explored whether massive eruptions can influence others across continents. The theory rests on the idea that the Earth's mantle, though solid rock, behaves over long timescales like a fluid. Pressure waves and shifts in heat flow could, in principle, connect distant hotspots. While evidence for such global triggers remains debated, certain patterns in the geologic record are difficult to ignore. Clusters of great eruptions sometimes appear close together in time, as though the Earth itself went through spasms of activity that reshaped entire eras. For example, during the end of the Permian period, the Siberian Traps erupted on a scale so vast that it blanketed much of Eurasia in lava. Around the same time, other volcanic provinces showed heightened activity, raising questions of whether one outpouring stirred the mantle in ways that affected others. More recently, the eruption of Tambora in 1815 occurred during a century of elevated volcanic activity worldwide, suggesting that certain eras may carry pulses of unrest. Yellowstone, with its immense size and deep roots into the mantle, could theoretically send ripples through this interconnected system, perhaps awakening other giants slumbering far from its caldera. The global consequences would then multiply. It would not be a single eruption reshaping climate, but a chorus of volcanoes adding their voices to the haze. Additional ash and gases would thicken the atmosphere's veil, prolonging the cooling and dimming of the skies. Agriculture, already strained, would face even harsher conditions. Oceans, already altered by the fallout of Yellowstone, would suffer further disruptions in chemistry and currents. Life would find itself tested not by one disaster, but by the possibility of many. Even if such chain reactions never occurred, the idea alone underscores the scale of Yellowstone's potential. A single eruption could shake fault lines nearby and disturb volcanoes half a world away. It reminds us that the Earth is not a collection of separate pieces, but a single, restless organism. What happens in one place can echo across continents, reverberating through stone, sea, and sky. And while these echoes spread through the ground, the air above would be carrying its own burden. For the gases released by Yellowstone would begin their long, dangerous work on the balance of the atmosphere itself. When magma meets the surface, it does not only release molten rock and ash, it breathes out gases, invisible yet powerful, capable of reshaping the climate of the entire planet. These gases are the true voice of the Earth in eruption, carried high into the atmosphere, where they linger and alter the balance of heat and light. A Yellowstone supereruption would unleash not only a flood of ash, but vast clouds of gases that could shift the trajectory of the climate in ways both immediate and long-lasting. One of the most important of these gases is sulfur dioxide. When released in small amounts, it may only irritate the lungs of those who breathe it, but when poured into the stratosphere in colossal volumes, it transforms the skies themselves. There, sulfur dioxide reacts with water vapor to form aerosols, fine droplets that scatter sunlight back into space. The result is global cooling. In the years after Pinatubo erupted in 1991, the planet cooled by about half a degree as sulfur aerosols circled the Earth. After Tambora in 1815, the cooling was so severe that crops failed, and the world endured the infamous year without a summer. From Yellowstone, the release of sulfur would dwarf those past eruptions, spreading a haze that could lower global temperatures by several degrees, enough to plunge the Earth into a deep volcanic winter. Yet while sulfur dioxide works to cool the world in the short term, carbon dioxide, another gas exhaled in vast quantities during eruptions, pushes in the opposite direction. Unlike sulfur aerosols, carbon dioxide is not washed away from the atmosphere in a matter of years. It lingers for centuries, trapping heat, thickening the blanket around the planet, and driving long-term warming. Volcanoes throughout history have released carbon dioxide, but in smaller eruptions, the effects were too limited to leave much trace. A Yellowstone-scale event could tip the balance, creating a future where, after the haze clears and the Earth slowly warms again, the atmosphere might be left holding higher levels of greenhouse gases than before. This creates a delicate paradox. The short-term consequences of the eruption would be cooling, the sudden plunge of temperatures, the dimming of the skies, the collapse of harvests under cold conditions. But the long-term legacy might be quite different, a slow rebound into a warmer world, driven by the accumulation of carbon dioxide that remained long after the sulfur aerosols had rained away. The Earth could first feel like it had entered a new ice age, only to emerge decades later into a greenhouse climate. The interplay of these forces is difficult to predict, for it depends on the amounts of gas released, the height to which they rise, and how long they linger. Scientists use models to test scenarios, imagining the injection of hundreds of millions of tons of sulfur dioxide into the stratosphere alongside immense volumes of carbon dioxide. The results are sobering. In nearly every case, the planet would endure years of dramatic cooling, followed by uncertain centuries of warming. The survival of societies would hinge not only on how they weathered the cold, but on how they adapted to the shifts that followed. The oceans, too, would feel the breath of Yellowstone, sulfur falling back to the surface as acid rain would change the chemistry of lakes and rivers, harming fish and poisoning fresh water. Carbon dioxide dissolving into the seas would make them more acidic, eroding the shells of tiny organisms that form the base of the marine food chain. The gases would not only affect the air above, but the waters below, linking atmosphere and ocean in a chain of disruption that stretched far beyond the initial eruption. These gases remind us that the power of Yellowstone lies not just in the violence of its eruption, but in the invisible legacy it would leave behind. The Earth's breath, exhaled in fire, would cool and then warm the planet in rhythms that no human hand could control. It would challenge civilizations not only to endure the first years of volcanic winter, but to navigate the centuries of climate that followed, shaped by a balance as fragile as it was immense. And as these gases reshaped the air and the oceans, the timeline of recovery would stretch outward, raising questions not only about survival in the present, but about how long it would take for the Earth to heal and life to return to something resembling balance. Once the eruption had ended and the fountains of fire fell silent, the world would not immediately return to normal. The first ash would settle, but the consequences would linger, etched into air, water, and soil. Recovery from an event of such magnitude is not measured in days or months, but in decades and centuries, with every stage of healing carrying its own trials. The earliest years would be marked by the volcanic winter. Sulfur aerosols high in the stratosphere would continue to reflect sunlight back into space, keeping the planet colder than usual. Even after the skies began to clear, the chill would linger, like a memory that refused to fade. For perhaps 10 or 20 years, the rhythm of the seasons would remain muted, summers too cool, winters too harsh. Agriculture would stumble again and again, never quite regaining its balance, and each harvest would be shadowed by uncertainty. But volcanic winters eventually ease. Sulfur particles, though powerful, do not last forever in the upper atmosphere. They fall slowly back to Earth, washed away by rain and snow. With time, the blue of the sky would sharpen again, the sunlight's warmth would return, and the immediate chill would fade. Yet this relief would not signal a full recovery. The ash that covered landscapes would take years to clear from rivers, roads, and farmland. Forests buried in layers of grit would grow back only slowly. Grasslands, stripped of their fertility, might take generations to return to their former richness. For ecosystems, the clock would tick more slowly still. Centuries might pass before balance returned. Forests would regrow, but not as they were before. Entire species could be lost, while others would rise to fill the empty spaces. In lakes and oceans, acidification from sulfur and carbon dioxide would linger, altering food chains at their base. The recovery of life is never about recreating what was lost, but about forming something new, shaped by the scars left behind. Just as the Earth reinvented itself after the Siberian traps and the Chicxulub impact, so too would it transform in the centuries after Yellowstone. Civilization's recovery would depend on its resilience. In regions hardest hit by ash and famine, populations would collapse or migrate, leaving behind abandoned cities and broken infrastructure. Some nations might fall entirely, their governments unable to manage the crises of food, power, and unrest. Others, more resourceful or fortunate in geography, might endure, adapting to the colder decades, finding new ways to grow food, and protecting their populations with stockpiles or technology. The future map of power and culture could look very different from the one that existed before the eruption. History offers glimpses of this truth. After Tambora erupted in 1815, recovery took years, but those years changed the course of nations. The famine and migration that followed shifted populations, altered economies, and even influenced art and literature. Now imagine those disruptions multiplied by the scale of Yellowstone. The decades of cooling, followed by the centuries of ecological change, would act like a sieve, testing which societies could endure and which would break under the weight of disaster. The story of recovery would not be a single path forward, but many paths diverging. Some regions might thrive sooner, using technology and trade to adapt to the altered climate. Others might sink into centuries of struggle, their histories marked by hardship long after the skies had cleared. Even the global atmosphere, though it would warm again as carbon dioxide lingered, would not return to exactly what it had been. The Earth, and humanity with it, would step into a new chapter, and as the world reshaped itself in this long recovery, those who survived would still live under the shadow of the caldera, aware that beneath the surface, Yellowstone's chambers of fire would one day fill again, preparing for another cycle in Earth's restless story. In the hours after Yellowstone's eruption, while ash spread across skies and rivers turned gray, the greatest struggles would fall to those living within North America itself. For millions of people, survival would depend not on distant trade routes or global cooperation, but on the daily question of how to breathe, how to drink, and how to endure the weight of ash pressing down on everything around them. The fallout zone, stretching for thousands of kilometers from the caldera, would be unlike anything most had ever imagined. Close to Yellowstone, the land would vanish entirely beneath meters of ash, burying forests, homes, and highways in a silent sea of stone dust. Farther away, the layers would thin, yet even a few centimeters could bring life to a standstill. Cars would clog with grit, water supplies would be poisoned, and lungs would choke on every breath. To live in this gray world would require strategies humanity has rarely had to attempt. Shelter would become the first line of survival. Those caught outside in the early storms of ash would struggle to find safety, for the fine particles are not like sand or dirt. Under a microscope, they are shards of glass, sharp enough to scar lungs and scratch eyes. Ordinary masks would do little to stop them. Survivors would need to seal themselves indoors, covering windows and doors, creating barriers to keep the ash from drifting inside. Basements and underground shelters would offer some of the best protection, not from fire or heat, but from the relentless rain of grit that filled the air for days and weeks. But sealing away the ash would not end the struggle. Water, normally so dependable, would quickly turn against its users. As volcanic ash mixed into rivers, lakes, and reservoirs, it would release chemicals that made the water unsafe to drink. Heavy metals and acids leaching from the particles would poison supplies, creating sickness in those desperate enough to drink from streams and taps. Filtration would be possible, but only with the right equipment. Basic filters would clog almost immediately, unable to handle the density of grit. To endure, people would need layered systems, boiling and filtering in sequence, or advanced technologies like reverse osmosis. For most, these tools would not be easily found. Air would demand its own defenses. Ash in the atmosphere would linger long after the initial eruption, stirred back into clouds by every wind. Breathing outdoors without protection would risk lasting damage to the lungs. Simple cloths or scarves would be nearly useless. Survivors would need advanced respirators capable of filtering the fine glassy dust, yet even those would fail quickly as the filters clogged. Supplies of clean masks would become as valuable as food itself, traded and guarded with desperation. The air of the fallout zone would turn every journey outside into a gamble, forcing people to choose between sheltering in place or risking exposure for resources. Even those who managed to endure the first weeks would face harder questions as time stretched on. Could life truly continue in regions blanketed by ash? Homes buried under heavy layers might collapse from the weight. Fields would remain sterile, sealed beneath crusts of volcanic debris that rain could not easily wash away. Livestock would perish from poisoned feed and water. Rivers choked with ash would kill fish and wildlife. The very land itself would resist habitation, not just for months, but potentially for decades. Scientists studying fallout maps predict that much of the western and central United States would be rendered uninhabitable in the immediate aftermath. Only the outer fringes of the continent might remain marginally livable, and even there, ashfall would still complicate every breath, every drink, every crop. The long-term question would not be how to stay in the fallout zone, but how to leave it. Mass migrations would begin, waves of people moving eastward or southward in search of clean skies and water. Cities beyond the heaviest ashfall would struggle to absorb them, their own supplies stretched thin. In the centuries that followed, nature would reclaim what was lost. Rains would slowly leach poisons from the soil, rivers would carve fresh paths, and forests might one day grow again over the buried plains. But for those alive in the first years and decades, the fallout zone would remain a place of silence and abandonment, a landscape where survival meant constant struggle against air, water, and ground that no longer supported life. And as survivors looked outward, leaving behind the gray shroud of the heartland, the burden of Yellowstone would not remain local. The global human cost would unfold across oceans, carried not only by the ash itself, but by the millions forced to flee their buried homes. When Yellowstone erupts, the devastation would not stop at the borders of North America. Its reach would be global, felt not only in the ash that circled the atmosphere, but in the movement of people, the strain on nations, and the weight placed on the human spirit. The first and most immediate sign of this would be the movement of people, millions leaving their homes in search of places where the air was clearer and the water was safe. These would not be small migrations, but waves of refugees, entire communities uprooted, traveling on highways choked with abandoned cars, or seeking refuge in towns already filled beyond their limits. In the past, history has seen human migrations sparked by droughts, famines, and wars, but never on a scale this vast. Families leaving the American heartland would push eastward or southward, some moving into coastal cities, others pressing into neighboring countries. Canada, Mexico, and even islands of the Caribbean would feel the pressure as populations sought new homes. But migration on such a scale does not happen smoothly. Borders, usually invisible lines on a map, would suddenly harden. Nations would struggle to decide how many people they could take in, and how to distribute scarce food and medical supplies among both citizens and newcomers. With resources shrinking, political tensions would flare. Governments faced with food shortages would prioritize their own populations, and trade agreements carefully built over decades could fracture within months. The ships that once carried grain across oceans might be redirected to serve only the wealthiest buyers, leaving poorer nations to face famine. Even countries untouched by ashfall would discover that their food imports had dried up, as harvests from faraway fields failed in the cooling climate. This strain would test the unity of nations, creating a new world order not shaped by armies or weapons, but by the need for bread, rice, and water. Amid this scramble for survival, health crises would grow. The ash that once darkened the skies does not simply vanish when it falls to the ground. Fine particles, sharp as glass under a microscope, would be carried by winds for years, lingering in the air even across continents. Breathing them in would scar lungs and inflame airways, causing widespread respiratory diseases. Hospitals would see waves of patients struggling with chronic coughing, asthma, and lung damage, yet many of those hospitals themselves would already be overwhelmed or even buried by ash. Countries far from Yellowstone would still see a rise in cases as the particles circled the globe, turning clean air into a hidden danger. The crisis of health would not be limited to lungs. Ash settling into rivers and lakes would seep into food chains, tainting crops, fish, and livestock. Communities relying on surface water would face outbreaks of sickness from contaminated supplies, forcing already struggling governments to stretch their resources further. With sanitation systems breaking down under pressure, diseases long thought to be under control could resurface, feeding on the chaos left behind by the eruption. Yet even beyond the hunger and the sickness, another burden would weigh heavily: the psychological toll. Humanity has always endured disasters, but few events compare to the scale of a supervolcano. The sight of a sunless sky, the endless twilight stretching day after day, would sink into people's minds like a shadow that never lifted. For children growing up in this new world, the memory of blue skies might become a distant story told by their parents. Anxiety, depression, and fear would spread as quickly as the ash itself, shaping the culture of entire generations. Communities forced to abandon their homes would struggle with the loss of identity, carrying only fragments of their former lives into new lands. Entire towns would vanish from the map, existing only in memory, leaving survivors with the haunting knowledge that they might never return. The psychological strain of displacement, of hunger, of watching loved ones fall ill, would create scars not visible in the ash, but carried in the minds of those who endured it. And while the fallout zone itself would stand as the epicenter of destruction, the global human cost would spread far wider. For some, it would be hunger; for others, sickness; for many more, the slow, heavy weight of fear that the ground beneath their feet was not as steady as they had always believed. As humanity faced these cascading struggles, the question would grow louder: if we cannot prevent such a disaster, can we at least prepare for it? That question would guide the efforts of scientists, governments, and ordinary people alike, leading to difficult choices about how to live with a danger that cannot be controlled. For as long as humans have faced natural disasters, we have asked the same question: can it be stopped? When it comes to Yellowstone, that question has drawn some of the boldest ideas in modern science. The thought of a supervolcano beneath our feet, vast enough to scar the world in a single eruption, almost demands that we imagine ways to tame it. Yet the very scale of Yellowstone makes such efforts not only difficult, but perhaps impossible. One of the most often suggested ideas is drilling into the magma chamber to relieve the pressure. At first glance, it sounds simple, like letting steam escape from a boiling pot. But the reality is far more dangerous. The rock above Yellowstone's chambers is miles thick, and the magma beneath is not a calm pool of liquid, but a vast reservoir under incredible pressure. Piercing that lid with drills could act not as a release valve, but as a trigger, opening new pathways for the molten rock to rise. Instead of preventing an eruption, such an attempt could bring it forward, setting off the very catastrophe it was meant to avoid. Another suggestion has been to cool the magma with water, flooding Yellowstone with enough liquid to sap its heat and lower the chance of eruption. Water does indeed cool rock, and in smaller systems, it has even been used to calm geothermal fields. But Yellowstone's magma chamber holds heat that has built up for hundreds of thousands of years, measured in scales so vast that no amount of human-engineered flooding could quench it. The water would turn instantly to steam, expanding violently and adding new stress to the fragile crust above the chamber. Instead of soothing the giant, such a plan could wake it. There are also theories about venting the gases slowly, creating artificial outlets that would bleed Yellowstone of its power over time. But volcanic systems are not like balloons that can be carefully deflated. They are networks of chambers, cracks, and conduits, shifting constantly under the immense forces of Earth's interior. Interfering with one pathway could simply redirect the pressure elsewhere, forcing magma into new cracks and destabilizing the system further. In this way, venting becomes less a safety measure and more like prodding at the gears of a machine whose workings we barely understand. Even NASA has weighed in, proposing a concept that captured public imagination. Their idea was not to stop Yellowstone in a single act, but to cool it gradually by injecting water deep into the ground. If enough heat could be drawn away over thousands of years, the theory went, it might prevent the buildup of energy that leads to eruptions. But this plan carries enormous flaws. The amount of water needed would be staggering, more than entire rivers could provide. The engineering required to drill so deep into unstable rock would be a feat unlike any ever attempted. And perhaps most troubling, even a small mistake in execution could cause a fracture, opening a pathway that would unleash the eruption immediately rather than centuries from now. The truth is that Yellowstone cannot be controlled. It is a force that exists on a timescale far beyond our planning, shaped not by human hands, but by the slow churning of Earth's mantle. Our machines, our drills, our theories are as fragile as twigs against the power stored beneath that caldera. What we can do is watch, measure, and prepare. Instruments can detect ground movement, gases, and tremors, giving us precious warnings. But to imagine that we could ever silence Yellowstone itself is to misunderstand the nature of the Earth. It is not a machine to be fixed, nor a fire to be extinguished, but a living system whose cycles unfold over millions of years. And so the challenge is not to stop it, but to live with the knowledge of its presence, a reminder that beneath our feet lies one of the greatest powers the planet has ever known. Yellowstone is not the only place where the Earth keeps extraordinary power close to the surface. Across the planet, other vast calderas rest beneath forests, cities, and seas, each one shaped by eruptions that changed landscapes far beyond their horizons. To look at them is to widen the map, to see Yellowstone as part of a larger family of giants that have been quietly sculpting the world for a very long time. On the North Island of New Zealand, a chain of steaming valleys and shimmering lakes traces the Taupo volcanic zone. At its heart lies Lake Taupo, a calm blue expanse filling a great caldera. The land around it is alive with heat. Geysers pulse, mineral terraces glow white in the sunlight, and hot rivers thread through forests of ferns. Scientists map old ash layers here that reach far out into the Pacific, a sign of past events large enough to alter skies across oceans. The piece on the lake's surface hides a complex system beneath, a network of magma and fractures that still sends gentle quivers into the hills and feeds the springs that breathe along the shoreline. Far away in southern Italy, the ground itself seems to inhale and exhale. Campi Flegrei, the Phlegraean Fields, is a broad caldera that stretches beneath neighborhoods west of Naples. Streets run past warm fumaroles. Ancient Roman walls stand near bubbling mud pools. Over years to decades, the land rises by centimeters and then settles again, a restless motion known as bradyseism. The harbor at Pozzuoli has lifted and sunk within living memory, moving old piers away from the tide. This is a city built on a thin skin above heat and gas, where careful instruments watch for changes in ground tilt and composition of the breath that escapes from the earth. In the United States, east of the Sierra Nevada, lies another quiet giant, the Long Valley Caldera. Meadows spread across a wide basin rimmed by pale cliffs of tough, rock welded together from ancient ash. Hot creeks wind through willows and sage. To the casual traveler, the basin looks like a high country pasture. To geologists, it reads like a page from a deep book, a place where a single eruption left a mark big enough to shape an entire valley. Today, a web of seismometers and satellite measurements keeps watch on the region, recording subtle swarms of earthquakes and the faint lifting and settling of the ground that speak to heat and fluids moving far below. Across the Sea of Japan, central Kyushu bears the Aso caldera, one of the largest in Asia. Villages, fields, and roads all lie inside its broad rim, with a smaller, active crater perched near the center. On cold mornings, steam drifts from vents like breath, and warning signs mark trails near the summit where gases can pool. The soils here are famously fertile, dark, and rich, feeding herds and crops that thrive on minerals from the old ash. The landscape tells two stories at once, one of danger and one of renewal, layered together in the same fields. Far older scars exist as well. In the mountains of Colorado, the La Garita region holds the remnants of a caldera formed in deep geologic time. The cliffs of the San Juan Mountains reveal thick stacks of welded tuff, the cooled remains of ash that once flowed like glowing rivers. No one was here to witness that ancient event, yet the rock remembers. These stone layers teach how a single eruption can strip hills, fill valleys, and build entire new plateaus that endure for millions of years. These calderas are not lonely curiosities, they are pieces of a global pattern. Each one sits above plumbing that runs down into the crust, where heat from the mantle melts rock and sends buoyant magma upward along faults and fractures. Each one leaves signals that patient instruments can read. Slight changes in ground height, bursts of tiny earthquakes, shifts in the balance of gases rising from vents and springs. Together, these places remind us that Earth's surface is thin and flexible, and that the deeper engine never truly stops. Why then does Yellowstone so strongly grip the imagination? Part of the answer is proximity to modern life. Yellowstone rests in the middle of a continent webbed with highways, power lines, farms, and cities. Its breath is visible to millions of visitors each year in columns of steam, in bright thermal pools, in the steady voice of geysers. Few other calderas allow people to stand so close to such clear signs of inner heat while remaining inside a national park with roads and boardwalks. Beauty and risk share the same stage, and that contrast makes the story unforgettable. Another part is connection. An eruption from a remote island might feel far away to many. Yellowstone sits inside a tightly linked economy where shipments, energy, and information flow hour by hour across states and borders. Any change in the land there would ripple through supply chains and skies quickly, which makes the abstract idea of a caldera feel more immediate to those who do not live beside one. Seen in this wider context, Yellowstone is one chapter in a larger book. Taupo, Campi Flegrei, Long Valley, Aso, La Garita, and others write their own lines about heat, pressure, and time. Their quiet present is not a guarantee of a quiet future, yet their pasts also show that landscapes heal and life returns. Understanding them as a family helps us see patterns that no single place can show alone. From this atlas view, it is natural to turn the lens from land to life. Stones, lakes, and tuff layers record eruptions, but so do living things. The next signs are not carved only into cliffs. They are tucked into ice, buried in sediments, and carried within us. To understand what one great eruption can mean for a species, we look to the traces left in memory deeper than history. The Earth remembers in ways deeper than any written history. Its memory lies hidden in layers of ash, in bubbles of ancient air trapped within ice, in sediments pressed into stone, and even within the fragile code of life itself. When scientists dig into these records, they uncover not just the story of continents and oceans, but also the scars left by cataclysms that nearly ended the story of life as we know it. One of the most haunting of these memories belongs to a single eruption, one so immense that it darkened the skies across half the world and may have pushed humanity to the brink of extinction. That eruption was Toba. On the island of Sumatra in Indonesia, a calm lake now stretches wide and still, reflecting the clouds and forests around it. But beneath its placid waters lies the caldera of a supervolcano that erupted about 74,000 years ago. The Toba eruption was one of the largest known in the last 2 million years. Geological evidence suggests that it expelled thousands of cubic kilometers of ash, enough to cover vast regions of Asia in a thick gray blanket. Traces of this ash have been found across India, China, and as far as Africa, showing how the eruption's reach extended across continents. But it was not only the ash that mattered. The eruption sent sulfur and other gases high into the stratosphere, where they reflected sunlight back into space. For years that followed, the Earth's surface cooled dramatically. Rainfall patterns shifted, monsoons failed, and fertile lands turned barren. Scientists believe this global disruption triggered a volcanic winter that may have lasted for decades and whose effects rippled across centuries. The memory of Toba is written not only in the rocks, but also in the climate records held within ice. Deep in Greenland and Antarctica, ice cores preserve ancient layers of snowfall compressed over tens of thousands of years. Within these layers are tiny bubbles of trapped air, each a time capsule of the atmosphere. Around the time of Toba's eruption, these cores show sharp drops in temperature. Chemical traces of sulfur confirm that a massive injection of volcanic gases had entered the sky. The timing aligns perfectly with the geological layers of ash found across Asia, weaving together a consistent picture of an Earth transformed by a single event. For our ancestors, the consequences were immediate and brutal. Imagine small groups of hunter-gatherers scattered across Africa and Asia. They relied on plants that sprouted with the rains and animals that followed the seasons. When the skies dimmed and the land cooled, harvests failed, herds shrank or migrated far from familiar grounds, rivers filled with ash, and lakes turned toxic. To survive, people may have huddled together in caves, their fires flickering faintly against the walls, while the world outside grew hostile and gray. The most compelling evidence of this struggle lies not in the ground, but within us. Genetic studies suggest that around 74,000 years ago, the diversity of the human population shrank dramatically. Instead of millions spread across continents, there may have been only a few thousand breeding individuals left to carry humanity forward. This genetic bottleneck is like a narrow passage in time, a moment when our species almost vanished. Every person alive today may trace their ancestry back to those survivors, whose resilience allowed humanity to endure one of the greatest natural disasters in history. There is still debate about just how severe this bottleneck was. Some scientists argue that the reduction in human diversity was less extreme than once thought, and that other factors may have played a role. Yet even if the details remain uncertain, the coincidence between the timing of the Toba eruption and the genetic bottleneck is too striking to ignore. It suggests that supervolcanoes are not just geological curiosities, but forces that have shaped the very course of human evolution. The scars of Toba can also be traced across the Indian Ocean and beyond. Sediment cores taken from the seabed reveal layers of ash that settled thousands of kilometers from the source. These layers provide a timeline of how far and fast the debris spread, giving scientists a clearer view of the eruption's unimaginable scale. They tell us that the eruption did not just affect a region, it disrupted the entire planet's systems, sending shockwaves through ecosystems and societies long before civilizations were even born. What makes Toba so haunting is not only its scale, but also its reminder of how fragile life can be in the face of Earth's power. Our species, still young and vulnerable, survived by chance and resilience. The whispers of that survival live on in our DNA, in the narrowing of genetic variation, in the faint but measurable marks of near extinction. Toba was not the first super eruption, and it will not be the last, but it remains one of the closest times humanity has come to disappearing entirely. As scientists study Toba's legacy, they gain insight into what future eruptions might bring. The ash, the gases, the long winters, the narrowing of survival. These are not distant myths, but real possibilities written into Earth's past. And in understanding Toba, we glimpse what Yellowstone or another supervolcano might mean for our world today. If Yellowstone were to erupt, the first shock would be measured in explosions and ash, but the true challenge for humanity would come after the skies darken and the earth grows cold. Survival would no longer be about resisting the immediate force of the eruption, but about enduring the long shadow it would cast upon the planet. In such a future, the question becomes not whether humanity could survive the first day, but whether it could adapt to the years that would follow. One vision of survival lies underground. Across the world, engineers and scientists have imagined how food could be grown in sealed environments, shielded from the choking ash and freezing temperatures above. In theory, vast tunnels and caverns could be converted into farms, with crops nurtured by hydroponic systems and warmed by geothermal energy. Instead of fields stretching under the sunlight, humanity would rely on racks of plants stacked high in the dim glow of artificial light. Such methods are not just speculation. Underground farming has already been tested in small scales in abandoned mines and urban basements where lettuce, mushrooms, and potatoes thrive without a single ray of natural light. Artificial lighting, however, is not a simple replacement for the sunlight. The energy needed to sustain crops at a planetary scale is enormous. Vast amounts of electricity would be required to power the lamps that trick plants into growing, and this raises the question of where that power would come from in a world shaken by volcanic winter. Some propose nuclear reactors as lifelines, steady sources of energy unaffected by the darkness above. Others imagine tapping into geothermal energy, especially near volcanic regions where the earth itself offers warmth. Yet even with these solutions, the limits of technology become clear. Feeding billions underground would demand resources and organization on a scale humanity has never achieved before. Stockpiles of food are another imagined safeguard. Many nations already keep reserves of grain, rice, and corn for emergencies, but these are meant to last months, not years. If Yellowstone erupted, the global food supply would collapse as harvests fail season after season. Stockpiles would run dry quickly, and decisions would need to be made about who receives them and how they are distributed. This scarcity would not only test our technology, but also our capacity for cooperation. Without careful management, food reserves could spark conflict instead of saving lives. Some scientists suggest that survival might depend on carefully chosen lifeboats of humanity, communities equipped with enough supplies and technology to endure the long winter. These groups might live in sealed habitats, cultivating crops under lamps, recycling water, and breathing filtered air. They would be small outposts of life, carrying the torch of civilization through the darkness. Such visions are sobering because they highlight the limits of what can truly be preserved. A handful of humans could survive, but the vast interconnected systems of modern life would falter. Cities, trade routes, and cultures that stretch across the globe could fragment, leaving behind only fragments of what once was. Yet history reminds us that survival is possible even in the harshest climates. Ancient humans endured the cold after Toba's eruption, clinging to life with far fewer tools than we have today. They had no electricity, no underground farms, no stockpiles guarded in silos, and yet they managed to carry the human story forward. By comparison, modern humanity has knowledge, technology, and foresight that could be harnessed to give us an edge in endurance. Still, the weight of billions of lives makes the challenge greater than ever before. The possibility of survival, then, is not simply a question of engineering or biology. It is also about social resilience, the ability of communities and nations to work together under stress that would shake the very foundation of civilization. Underground farms and glowing crops might sustain some, but the greater challenge would be ensuring fairness, preventing collapse, and carrying culture forward while the skies remain dim. From this view, Yellowstone is not only a geological threat, but a mirror held up to humanity's strengths and weaknesses. The survival of our species in such an event would not depend solely on the ingenuity of machines or the size of our food reserves, but also on how we choose to share them, how we organize in the face of scarcity, and how we endure the years when the earth itself seems unwilling to provide. To live near Yellowstone is to live with a quiet awareness, a background hum of possibility that never quite fades. For people in Wyoming, Montana, and Idaho, the supervolcano is not an abstract concept on a map, but part of their daily landscape. Families grow up beneath its mountains and forests, ranchers work its valleys, and children learn about its geysers and hot springs in school. Alongside that beauty, there is also knowledge that beneath the ground lies one of the most powerful volcanic systems on Earth. Most of the time, it feels distant, like a story that belongs more to textbooks than to the present moment. But every so often, when the ground trembles with swarms of tiny earthquakes, or Old Faithful behaves in unusual ways, that quiet awareness rises into something sharper, something closer to dread. Psychologists know that humans are wired to fear what they cannot control. An asteroid streaking through the sky is dramatic but visible, and its threat feels like something we could prepare for. Yellowstone is different. It hides in silence, biding its time in chambers of molten rock that no one can see. There are no visible countdowns, no ticking clocks that tell us how much time is left. This uncertainty is fertile ground for fear. People do not know whether the eruption will come in 10,000 years or in 10 weeks, and that ambiguity alone makes it more unsettling than many other natural threats. Communities close to the park carry this tension in quiet ways. Local news outlets sometimes run stories when scientists report unusual ground uplift or when earthquake activity spikes, and suddenly the public's imagination takes over. Supermarket shelves are not emptied, but conversations in cafes and schools turn toward what if. For those living farther away, Yellowstone feels like a distant curiosity. For those nearby, it is the invisible neighbor, present even when silent. Fear often thrives in the absence of certainty. When people cannot know exactly what is coming, their minds fill in the blanks with worst-case scenarios. This is why misinformation about Yellowstone spreads so quickly. Social media posts and tabloids often claim the supervolcano is overdue, or that scientists are hiding warnings of an imminent eruption. The reality is far more nuanced. But nuance rarely travels as fast as fear. In this way, the psychology of waiting becomes as important as the geology itself. Managing the narrative is part of managing the hazard. Scientists face a delicate task in communicating about Yellowstone. They must inform the public about what is real, about the constant monitoring of earthquakes, ground deformation, and gas emissions, while also preventing panic. Too much reassurance, and people stop paying attention. Too much alarm, and fear spirals beyond reason. Volcanologists and agencies like the U.S. Geological Survey balance on a thin line, sharing data and context, reminding the world that Yellowstone is active but not erupting, restless but not catastrophic. For many, this balance is hard to accept. Fear does not always listen to reason. People want definitive answers, dates circled on calendars, clear signals of when to prepare. Yellowstone offers none of these. It sits in geological time, vast and unbothered by human impatience, while people live in short spans of years and decades. That mismatch creates tension that seeps into culture, media, and even art. Yellowstone appears in movies, novels, and speculative documentaries, not just because of its scientific importance, but because it resonates with something deeper in the human psyche: the dread of a threat we cannot prevent. The fear of waiting is not limited to those who live near the park. Around the world, people who learn about Yellowstone often describe a similar unease. It is a reminder that Earth is alive and that its greatest forces lie beyond human command. In this way, Yellowstone is more than a geological hazard. It is a mirror reflecting the limits of our control and the fragility of our place on the planet. That fragility is not paralyzing, but humbling. It shapes how scientists talk about their work, how communities prepare for rare but devastating events, and how humanity confronts the unknown. The psychology of waiting, of living with a risk that cannot be erased or controlled, becomes its own kind of challenge, one that exists not in the rocks, but in the human mind. And just as Yellowstone continues to breathe quietly beneath the surface, people continue to live above it, carrying that quiet fear, that invisible weight, as part of their story. The question of timing is one that lingers in the human mind, pressing for certainty where none can be given. Yellowstone's history offers patterns, but patterns in geology do not work the same way as the ticking of a clock. The last three great eruptions came roughly 600,000 to 800,000 years apart. Some people look at that spacing and calculate that Yellowstone is overdue. It is an idea that spreads easily because the human brain is built to search for cycles and to mark time in predictable beats. Yet the Earth does not measure its life in such tidy rhythms. The truth is that probability is not the same as schedule. The spacing of past eruptions does not create an appointment on the calendar of the Earth. Yellowstone is not late nor early, because in geological terms there is no exact deadline. The molten rock beneath the caldera will erupt only when pressure and conditions align, not when the pattern tells it to. This is one of the humbling lessons of geology. The Earth's rhythms stretch across spans so vast that human lifetimes, and even civilizations, seem like brief flickers against them. Scientists at the United States Geological Survey and the Yellowstone Volcano Observatory spend their days and nights watching for the smallest hints of change. Networks of seismographs dot the region, listening to the tremors that ripple under the ground. These are not the grand earthquakes that topple cities, but swarms of tiny shakes, some lasting days or weeks, like the restless murmurings of a giant beneath the surface. GPS stations track the rise and fall of the land itself, measuring movements so small they are invisible to the eye. Some years the ground swells upward by a few centimeters, then later settles back down, as though the earth is breathing slowly. There are also the gases, drifting unseen from vents and pools, carrying messages from the depths. Scientists measure sulfur, carbon dioxide, and other emissions to read the conditions below. Each whiff of gas is like a letter written from the hidden chambers, telling us whether pressure is building or easing. When combined, these signals form the only early warning system we have. Yet even with this web of instruments, prediction is far from exact. Volcanoes are not machines with gauges that reveal a single truth. They are complex systems where one change can mean many things and where silence can be as mysterious as noise. The scientific consensus today is that there are no signs of an imminent eruption. Yellowstone is restless, as it has always been, but its activity is no greater now than in the centuries before. The swarms of earthquakes, the uplift and subsidence of the ground, the shifting geysers, all of these are part of the natural rhythm of a living volcanic system. To the scientists who study it, the evidence shows no eruption waiting just around the corner. And yet, the clock of geology is still ticking, even if we cannot read its exact hands. Yellowstone has erupted in the past, and it will erupt again, whether that will be in our lifetime, in the lifetime of our grandchildren, or in 10,000 years, remains unknown. This uncertainty itself is what unsettles us. We are creatures who find comfort in knowing, in planning, in preparing for dates and deadlines. Yellowstone offers no such clarity. It sleeps in silence until the day it chooses not to. This lack of precision is what makes living with Yellowstone both manageable and haunting. It reassures us that nothing is about to happen tomorrow, yet it reminds us that someday, on a timescale larger than our own, the cycle will continue. And so, humanity lives above this giant, with the knowledge that it could remain still for thousands of years, or that it could stir again far sooner than expected. That uncertainty, the waiting without knowing, is perhaps as powerful a weight on the human imagination as the eruption itself would be. Preparation for an event as vast as a Yellowstone eruption cannot mean prevention. The forces beneath the caldera are far beyond human control. What preparation can mean, however, is readiness, the ability to soften the blow, to give humanity its best chance of enduring the long shadow such an eruption would cast. Scientists, planners, and communities imagine what steps could be taken, not to stop the inevitable, but to face it with knowledge and foresight. The first layer of preparation lies in early warning. Every tremor, every subtle rise of the land, every change in the gases escaping from Yellowstone is part of a larger story unfolding beneath the surface. Networks of seismographs, GPS stations, and gas monitors record these signals in real time, feeding them to scientists who watch for patterns that might mark the approach of something greater. While no system can predict the exact day or hour, these instruments could offer days or even weeks of warning before an eruption. Such a window would be invaluable, allowing for global alerts to be sent, for flights to be grounded, for emergency stockpiles to be unlocked, and for communities in the fallout zone to brace themselves for what is coming. The importance of even a brief warning cannot be overstated. A few days might mean the difference between chaos and coordination, between panic and measured response. It is the fragile margin in which lives could be saved, not by stopping the eruption, but by giving people the time to prepare for its consequences. Beyond the warning systems, civil defense and emergency planning would become the backbone of survival. Governments would need to act swiftly to secure stockpiles of food, medicine, and clean water, ensuring they are not lost in the first waves of ash and disruption. Vulnerable infrastructure, such as power grids, water supplies, and hospitals would need protection, for even the smallest interruptions could cascade into disasters when layered atop the volcanic crisis. Evacuations would be among the greatest challenges, as millions of people live in zones where heavy ashfall would render homes uninhabitable. Roads would clog, airports would close, and entire regions would have to be moved away from danger zones with only days to spare. The scale of such a task is almost unimaginable, yet it is one of the realities scientists and planners must face when they consider Yellowstone. Even beyond the immediate evacuation, agriculture would face its own battle. A volcanic winter could last years, with shorter growing seasons and weaker sunlight crippling crops worldwide. To prepare for this, grains and seeds could be stored in advance, kept in vaults and silos as insurance against years without summer. Plant scientists have also imagined developing crops capable of surviving in cold or low-light conditions, strains that could grow in the dim twilight that might follow such an eruption. Underground farming, powered by artificial light, could become more than an experiment, it could be a necessity. By preparing now, these methods could be scaled when the world most desperately needs them. No single nation could face this alone. Yellowstone's eruption would not stop at the borders of the United States. Its ash and gases would travel across oceans, dimming skies on every continent, straining food supplies, and reshaping global trade. This is why international cooperation would be essential. Shared stockpiles, coordinated food distribution, and agreements on energy and medicine would be needed to prevent collapse. In the same way humanity has treaties for nuclear weapons and climate change, some scientists argue there should be a global survival plan for supervolcanoes, a recognition that this threat belongs to all of us, not just those who live nearby. Yet preparation is not only physical, it is also psychological. Fear spreads faster than ash, and panic can collapse societies faster than hunger. People must be prepared not only with supplies, but with understanding, so that when warnings come, they respond with action rather than despair. Education about Yellowstone's risks, clear communication from scientists, and transparency from governments could help foster trust and resilience. Communities that understand what is happening are less likely to give way to rumors and more likely to endure together. In this sense, mental resilience is as important as grain reserves or water filters. The idea of preparing for Yellowstone is daunting, yet it is also a reminder of what humanity can do when it chooses to plan for the unthinkable. Early warnings, emergency systems, agricultural innovations, international cooperation, and psychological preparedness. These are the tools that might carry us through. And as scientists and planners continue to refine these strategies, they remind us that even when the Earth moves in ways beyond our power, we still have choices in how we face it. Amidst all the talk of cataclysm and hidden danger, it is easy to forget that Yellowstone is also one of the most beautiful places on Earth. It is a land where fire and water meet, where steam curls into the cold morning air, and where colors bloom in pools so vivid they seem painted by another world. This surface beauty is the everyday face of a restless giant, and it tells us as much about the forces below as any seismograph or gas monitor ever could. The most famous voice of Yellowstone is Old Faithful, the geyser that has erupted with remarkable regularity for centuries. Tourists gather in silence on its boardwalks, waiting for the moment when the earth exhales in a towering plume of boiling water and steam. Beneath this display is a complex rhythm of groundwater seeping deep into the earth, heating against magma-warmed rock, and then bursting skyward when pressure can no longer be contained. Old Faithful is only one among hundreds of geysers in the park, but its predictability has made it a symbol, a reminder that Yellowstone is alive and breathing. Each eruption is not only a spectacle, but also a small message from the hidden magma chamber far below. Alongside the geysers lie the hot springs, shimmering pools where minerals paint the earth in surreal palettes. Some are deep turquoise, others ringed with reds, oranges, and yellows, their colors created by heat-loving microbes that thrive in waters too extreme for most life. The Grand Prismatic Spring, Yellowstone's largest, spreads in a vast circle of radiant color, so bright it can be seen from the air. Standing before it, one sees not only a wonder of nature, but also a direct expression of the planet's inner heat rising to the surface. These springs are gentle compared to the violence of an eruption, yet they are born of the same fiery source. Boiling mud pots, hissing fumaroles, and steaming rivers add to this symphony of geothermal activity. They are constant reminders that Yellowstone sits on the edge between creation and destruction. Each bubble of mud and each plume of steam is a whisper from the giant below, showing us the incredible energy stored beneath our feet. Even as people marvel at these wonders, the ground beneath them is shifting, alive, and waiting. What makes Yellowstone so unique is this dual nature. Above, it is a sanctuary of beauty. Herds of bison graze in meadows dotted with wildflowers. Wolves move quietly through the forests, and bears wander across open valleys. Rivers cut through canyons of gold and orange rock, and waterfalls plunge with graceful power. The surface feels like a paradise, a preserved fragment of wild America, yet below lies something capable of rewriting climates, shaping continents, and testing humanity itself. This tension between surface and depth is part of Yellowstone's enduring allure. People come to see the geysers and hot springs, yet even if they do not always say it aloud, they know what lies beneath. The beauty is inseparable from the danger, and perhaps that is why it fascinates us so deeply. To stand on Yellowstone's soil is to stand above one of the greatest sources of destruction the earth holds, and yet to see only forests, rivers, and colors that dazzle the eye. Every steaming vent, every burst of Old Faithful, every shifting hue in a hot spring is a gentle reminder of what simmers below. The awe of Yellowstone is not diminished by its risk. If anything, the two feed one another. Its beauty feels sharper because we know it is fragile, resting above chambers of fire. Its danger feels greater because it hides beneath something so breathtaking. In this way, Yellowstone is both gift and warning, a place where Earth shows us its splendor and its power in the same breath. Volcanoes are remembered most often for their destruction. They are mountains that shatter, skies that darken, and rivers of fire that consume everything in their path. Yet when the dust settles and the years pass, the story of a volcano becomes more complicated. For as much as they destroy, volcanoes also create. They are reminders that Earth's greatest violence often carries with it the seeds of renewal. The soil that nourishes so many of the world's most fertile lands began as ash, pumice, and lava. When a volcano erupts, it scatters minerals into the air and across the ground. In the first moments, this blanket seems only to suffocate. Crops die, rivers clog, and fields vanish under gray layers. But given time, that same ash weathers into some of the richest soils known to farmers. In Indonesia, rice terraces thrive on the slopes of volcanoes that once devastated the land. In Italy, vineyards flourish in the shadow of Mount Vesuvius, where grapes draw flavor from the minerals left behind by ancient eruptions. The cycle is slow and harsh, yet it is also generous. Out of fire and destruction comes life, vibrant and renewed. The paradox is striking. An eruption that brings famine and loss in one generation may bring abundance in the next. Lava that incinerates forests hardens into new rock, which over centuries crumbles into soils where new forests take root. It is creation through catastrophe, a rhythm as old as the earth itself. Without volcanoes, much of the land that sustains us would not exist at all. Islands like Hawaii were born entirely from lava rising from the sea, their beaches and valleys still young in geological time. Volcanoes also shape the air and waters around us. Gases released during eruptions can alter climates for years, but over longer stretches of time, they have balanced Earth's atmosphere. Carbon dioxide, emitted from countless eruptions over billions of years, has played a central role in warming the planet enough to sustain liquid water and life. Sulfur, while capable of dimming sunlight after an eruption, also cycles through oceans and soils in ways essential to living systems. In their chaos, volcanoes are also caretakers, replenishing elements that life requires. Yellowstone, with its dual face of beauty and danger, is part of this same paradox. Its hot springs and geysers are not only signs of hidden fire, but also fountains of minerals and heat that shape the ecosystems around them. Microbes thrive in its boiling pools, coloring the waters with brilliant rings of orange and green, hinting at forms of life that may have been present on Earth in its earliest days. Some scientists even study these organisms to imagine how life might exist on other planets. The same heat that one day could tear continents apart is, in the present, nurturing unique forms of life that teach us about survival itself. The creative power of volcanoes is written across the planet. The Andes, the Cascades, the Japanese archipelago, and entire stretches of the Pacific are chains of volcanoes that have built mountains, fed rivers, and given rise to fertile plains. Humanity has settled again and again on volcanic lands, drawn by their beauty, their fertile soils, and their promise, even while knowing the risk that comes with them. People build homes, plant crops, and raise families on slopes that will one day erupt again, living within the paradox because the rewards are too rich to ignore. To speak of volcanoes, then, is to speak not only of destruction, but of creation. They are reminders that the earth is never static, that the land beneath our feet is alive, reshaping itself in ways that both challenge and sustain us. In Yellowstone, as in Vesuvius or Toba, the paradox is always the same. What is taken in moments of fire may, across centuries, return as new life. The giant beneath our feet is both destroyer and giver, both a threat to survival and a source of renewal. And in this duality lies the essence of Earth itself, a planet where creation and catastrophe walk hand in hand. Yellowstone is a place where extremes meet. It is at once serene and restless, a wonderland of forests, rivers, and steaming pools resting above chambers of molten fire. It is a reminder that the earth beneath our feet is alive, that its surface is only a thin skin stretched over forces vast enough to shape continents and climates. Scientists call it a supervolcano, but to many who walk its valleys, it feels like a sanctuary of nature, a meeting ground of beauty and danger, of calm and catastrophe. To speak of Yellowstone is to acknowledge a paradox that runs through all of Earth's story. It is a sleeping giant, and like all giants, its presence is felt even when it slumbers. We cannot fight it, and we cannot control it. The magma beneath its surface does not answer to human will, and no engineering project can diffuse its power. What we can do is listen, measure, and try to understand. And perhaps, in that understanding, we find a kind of calm. Knowledge is not just a shield against fear, but a light that makes the unknown a little less overwhelming. The scientists who monitor Yellowstone are not waiting with panic, but with patience. Their instruments read tremors, their satellites trace movements of the land, their sensors catch the faintest whiffs of gas. Each signal is studied, each fluctuation weighed, not to stoke dread, but to learn. This is how humanity meets forces beyond its control, not with defiance, but with curiosity. To learn is to prepare. To ask questions is to stand a little steadier in the face of uncertainty. And Yellowstone invites questions. What would happen if it erupted in our lifetime? How would humanity adapt to years of volcanic winter? Could our technologies, our food systems, and our social bonds endure such a trial? Each of these questions stretches the imagination, pulling us into possibilities that are humbling, yet also deeply human. We imagine because we want to endure. We ask because we hope to answer. But Yellowstone is not only a story of danger, it is also a story of awe. Its geysers rise in towering plumes, its hot springs shimmer with colors born from life forms that thrive in extremes. Its valleys host herds of bison moving across landscapes older than memory. Tourists travel from across the world to witness this wonder, often without realizing that the beauty they see is only the surface of something far larger. It is a reminder that Earth is not a static planet, but one that breathes, shifts, and renews itself, often in ways that both terrify and sustain. And so we come to the reflection that lingers when all the facts and figures are set aside. Yellowstone is a sleeping giant. We cannot fight it, only understand it, and perhaps, in knowing, we find calm. To live on Earth is to live with uncertainty, but also with beauty. To walk upon Yellowstone's soil is to walk above fire, but also to stand among forests, rivers, and skies that have been shaped by that very fire. Creation and destruction are not opposites here, they are part of the same story. The story of Yellowstone, then, is not just about geology or risk, it is about perspective. It reminds us of how small we are against the planet's timescales, but also how resilient we can be when we choose to learn. It tells us that knowledge is the true antidote to fear, and that wonder can exist alongside uncertainty. If you have found yourself carried along by this story, perhaps you might join this little community of dreamers and learners. A gentle like, a quiet subscription, or a comment sharing where you are listening from tonight helps this journey continue. I love watching the map of the world light up in the comments, one listener at a time, scattered across countries and time zones, connected by curiosity and calm. So as Yellowstone rests in silence, let us rest in knowing. The earth beneath us holds giants, but it also holds beauty. And through science, through stories, and through the simple act of wondering together, we carry on.